How does a dying giant star collapse into a neutron star? What would it feel like to stand on such an impossibly dense surface? Could the cores of neutron stars hide exotic matter beyond anything we've ever seen? High above, the night sky stretches like a serene, dark ocean dotted with stars. It feels peaceful and eternal. But beyond that gentle, twinkling facade, the universe holds secrets, both beautiful and fierce. In the silent cosmic darkness, there are remnants of unimaginable explosions, tiny objects that pack the weight of suns, and events so intense they can warp space and time. These hidden characters in the story of the cosmos are neutron stars, the dense, mysterious cores left behind when giant stars live and die. Our journey will take us into the realm of these neutron stars. We will drift through their birth in stellar demise, feel the enormity of their density and gravity, sense the crackling power of their magnetic fields, and listen for the whispers of their pulses. We will even witness the rare cosmic ballet of two neutron stars spiraling together in a final, dramatic embrace. Through it all, we maintain a gentle pace, like an observer floating in space, calmly taking in the wonders and the fury from a safe distance. Let's begin where these celestial remnants are born, in the final moments of a massive star's life, when the quiet of the night sky is momentarily broken by the brilliant flash of a supernova. In the quiet darkness between the stars, a giant sun is reaching the end of its life. For millions of years it has burned brightly, forging heavier and heavier elements in its heart. Now, at last, it has nothing left to give. The fuel that sustained its brilliance is exhausted, and a deep stillness settles at its core. Without the outward push of energy from fusion, gravity seizes control. In a sudden, catastrophic moment, the core of the star begins to collapse in on itself. The inner layers rush inward at incredible speeds, compressing and heating under their own tremendous weight. At the very center, the temperature and pressure soar beyond imagination, and the star's iron heart crumples. Then comes the rebound. Like a cosmic drumbeat, the core's collapse halts abruptly as new forces stiffen resistance. The infalling material slams into this now unyielding core, sending a powerful shockwave rippling outward. In an instant, the star is torn apart from within. Its outer layers erupt violently into space, a supernova explosion blossoming into the cosmic night. For a brief moment, this dying star blazes brighter than an entire galaxy. The explosion casts stellar debris in all directions, lighting up the surrounding space with ghostly radiance. Yet, if one were watching from afar, they would witness this titanic event in eerie silence, an immense flash of light expanding in the vacuum without a sound. As the brilliant glow fades and the stellar ashes drift away, the chaos of the supernova gives birth to something new. Hidden in the wreckage is a survivor, the collapsed core of the star, now transformed into one of the strangest objects in the universe. In the aftermath's dimming fire, this newborn remnant emerges as a tiny ember of incredible density and power, a neutron star. This neutron star is unimaginably small compared to the once mighty star that gave it life. A sphere only about a dozen miles across, barely the size of a city, now holds more mass than our sun. It is a compact, crushed core, a stellar heart that endured the collapse. Inside it, matter has been pressed to extremes. Atoms no longer exist as they did in the star's golden days. Electrons and protons have fused into neutrons, packing the core so tightly that a single teaspoon of this material would weigh billions of tons. The newborn neutron star is incredibly hot, an ember left from the supernova's fury. It glows faintly in high-energy light, X-rays and gamma rays, as it cools from temperatures of millions of degrees. But to our human eyes, it would appear as a tiny, dark sphere, almost invisible amidst the expanding cloud of supernova debris, save for its ghostly glow. Surrounded by the expanding remnants of its former self, the neutron star sits quietly at the center of the supernova remnant. In time, that remnant will spread out into the interstellar medium, enriching space with heavy elements forged in the star's final moments. Those elements will drift and mix, possibly one day to become part of new stars, new planets, or even life. But at the center, the neutron star remains, a dense and lonely monument to the star that once was. This is how neutron stars are born, in violence and light, in the final collapse of a massive star. These cosmic embers of collapse carry within them the memory of the star's life and death. They are the condensed, preserved cores of stars, now embarking on a new existence in the darkness. Floating in space, the neutron star is like a celestial phoenix, a new form arisen from the ashes of its predecessor. It spins rapidly as the parent star's rotation has intensified during collapse, like a twirling ice skater pulling in their arms. Where the star might have spun once every few weeks, this remnant might now spin many times each second. Some newborn neutron stars rotate dozens of times per second, their surfaces moving at incredible speeds. In the silence of space, this dense sphere turns swiftly, carrying on the momentum of the star that birthed it. The environment around the newborn neutron star is extreme beyond comprehension. The gravity at its surface is overwhelmingly strong, hundreds of billions of times stronger than Earth's gravity. If an object were to fall onto that surface, it would slam down with unimaginable force. But in these early moments, there is little left to fall. Most of the nearby gas has been expelled in the explosion, leaving the neutron star alone in a bubble of expanding debris. For the star that has died, a new existence has begun in the form of this neutron star, an object that challenges our understanding and piques our curiosity. It is only the first stop in our journey to explore the wonders these dense stellar remnants have to offer. For all its unassuming size, the neutron star that remains is among the most extreme objects in existence. Consider this: an entire sun's worth of mass, in fact about 500,000 Earths, is crammed into a sphere no wider than a large city. The density defies intuition. If you could hold a piece of this star the size of a sugar cube in your hand, though nothing could actually contain such a piece, it would weigh roughly 1 billion tons. That is about the weight of a mountain compressed into something that would sit in your palm. Such is the incredible compactness of a neutron star. Standing on the surface of this dense survivor, if it were possible, would be an unimaginable experience. Gravity on a neutron star is hundreds of billions of times stronger than on Earth. A person who weighs 150 pounds on Earth would feel billions upon billions of pounds of force pinning them down on a neutron star. In truth, anything that attempted to land on the surface would be instantly crushed and obliterated. Even a falling pebble would strike the surface with the energy of an atomic bomb. The pull is so strong that to escape, one would need to travel at more than half the speed of light. Such an escape is far beyond any rocket's capabilities. Even light itself loses considerable energy trying to climb away from the star's grasp. The neutron star's surface is not like the surface of an ordinary planet or star. It is thought to have a solid crust, ultra-dense and remarkably smooth. Under gravity so intense, even mountains would be flattened. The tallest mountains on a neutron star might be mere inches high, tiny bumps on an otherwise featureless sphere. The crust is composed of tightly packed atoms, mostly iron and other heavy elements that were forged in the supernova. But even those atoms are crushed and deformed, forming a crystalline lattice under immense pressure. Just beneath that rigid crust, the pressures become so great that even atomic structure breaks down. The electrons are forced into the atomic nuclei, combining with protons to form more neutrons. The matter there transitions into an exotic ocean of neutrons, mixed with some remaining protons and electrons, a strange, dense fluid that lies beneath the solid surface. By all accounts, a neutron star's crust is the strongest material imaginable, able to withstand stresses that would annihilate any ordinary matter. Deeper still towards the center of the neutron star, the nature of matter grows stranger. The core might be a soup of mostly neutrons, squeezed so tightly that they begin to touch and overlap. Some theories suggest that in the innermost core, the distinction between individual neutrons might vanish, creating a sea of quarks, the fundamental building blocks inside neutrons and protons, all bound together in a single mass of ultra-dense matter. This could be a form of matter we have never seen directly, sometimes referred to as quark matter, or a strange star, if it were to exist on its own. We do not know for certain, because the conditions inside a neutron star are beyond what we can replicate on Earth. In these depths, the pressure is trillions of times greater than in an atomic nucleus, and atoms as we know them cannot survive. Imagine traveling downward from the neutron star's surface toward its center. In the first few centimeters, you would pass through a thin atmosphere, perhaps just a wisp of hydrogen or iron vapor clinging to the surface. Quickly, you'd encounter the solid crust, as hard as steel, 1 billion times over. This crust might be only a kilometer or so thick, yet it contains nuclei squeezed into odd shapes. Scientists poetically call some of these forms nuclear pasta, with names like gnocchi and spaghetti, because of the strange shapes nuclear matter may adopt under extreme forces. Beneath this crustal layer, the material becomes more fluid. A super-dense liquid of neutrons begins, stretching down into the core. In that neutron fluid, properties are unlike any normal liquid. The neutrons may move without friction, forming what's called a superfluid. If you could stir it, it would swirl forever, never settling, because there is virtually no resistance. And mixed in this fluid might be superconducting protons, meaning electricity could flow without resistance as well. The interior of a neutron star is, in a sense, a gigantic nucleus, and also a playground for quantum phenomena on a macroscopic scale. Every so often, as the neutron star ages and cools, the fluid interior and solid crust adjust, sometimes suddenly. A portion of the crust might crack or shift slightly as the star settles, analogous to a quake. On Earth, we have earthquakes. On a neutron star, these starquakes can be far more potent. A small shift in the crust can release an outburst of energy, sometimes detectable across the cosmos, as a flare of X-rays or gamma rays. From crust to core, the neutron star is a layered marvel of physics. The entire star is only around 10 to 20 kilometers across, yet within that small volume, it holds so much. The mass, the energy, the magnetic and rotational forces, all compressed. If you could shrink yourself and tour the inside, you would see transitions from solid to liquid-like states, from a landscape of nuclei to a sea of neutrons, and perhaps to the enigmatic core. At the surface, conditions are still extreme. The temperature of a young neutron star can be millions of degrees. Over time it cools, but even after tens of thousands of years, the surface can still be 100,000 degrees or more, faintly glowing in X-rays. Yet despite such heat, the star would appear almost pitch dark to our eyes, since it emits little visible light. If you were observing a neutron star from a safe distance in space, you might not see it at all unless you had instruments sensitive to high-energy radiation or radio waves. Only in certain conditions, like if it's an active pulsar or magnetar, does a neutron star announce itself strongly. Otherwise, it might just be a silent, nearly invisible ball of dense matter drifting through the darkness. To put the density into another perspective, human minds struggle with these magnitudes. If you took every person on Earth, all 8 billion of us, and crushed us into a single sugar cube-sized piece, that still would not approach the density of a neutron star. The matter in a neutron star is packed so tightly that a lump the size of a pebble would outweigh Mount Everest. This defies any experience we have. Even the core of atoms is not something we feel in daily life. Yet here it is, on a macroscopic scale. Nature has created a huge ball that is basically one enormous atomic nucleus. Because of this, the gravity of the neutron star warps the space around it. Light leaving the surface will follow curved paths, and an observer above the star might even see the backside of the star slightly, as light bends around under gravity's influence. Time itself runs differently near this dense mass. A clock set on the neutron star would tick slower relative to one far away, though an outside observer might never get to see that clock in action. Such effects, predictions of Einstein's theory of gravity, become very real in the vicinity of a neutron star. Yet, despite these extreme conditions, the neutron star is stable. It is held up by the quantum forces between neutrons, a quantum pressure that resists further compression. The neutrons refuse to be squeezed into an even smaller space, and this neutron degeneracy pressure is what prevents the star from collapsing further. Only if the neutron star were to gain significantly more mass, for example, by merging with another star or accumulating material from a companion, would it overcome this barrier and collapse into a black hole. But for now, the neutron star simply exists in a delicate balance. Gravity pulling inward ferociously, and the remnants of nuclear forces pushing outward to hold it up. These dense survivors of stellar death are incredibly long-lived. With no fuel to burn, they shine only from leftover heat and perhaps from occasional magnetic or rotational energy losses. Over millions of years, they will slowly cool and fade. But even after billions of years, a neutron star could still be warm compared to the space around it and remain a solid, compact object. Unless something disturbs it, it will continue drifting through the galaxy nearly forever, a spent core of a star that refuses to vanish. In the grand scale of the cosmos, neutron stars are tiny, but their significance far outweighs their size. They push physics to its limits, containing crushed matter that challenges our understanding of nature's laws. Each one is a cosmic vault, holding secrets about how matter behaves when pushed to the extreme. Through observing these dense survivors, astronomers and physicists glean insights about fundamental particles and forces. From the outside, though, one might simply marvel at the sheer improbability of their existence. A city-sized sphere, with the mass of a star, spinning rapidly, possessing gravity so intense it can slightly trap even light. It is both a monster and a wonder of the universe. At once a corpse of a star and a new, exotic world, all its own. Yet, as if neutron stars weren't extreme enough, some of them possess another astonishing property: magnetism on a colossal scale. While every neutron star carries a strong magnetic field, a select few are magnetic titans beyond all others. We call these extraordinary remnants magnetars. The very word suggests their defining trait. They are magnets on a stellar scale. A magnetar's magnetic field is so strong that it's almost beyond comprehension. Earth's magnetic field, which gently moves our compass needles, is utterly feeble by comparison. Even a typical neutron star may have a magnetic field trillions of times stronger than Earth's. But a magnetar's field can be another 1,000 times stronger still. Picture a magnetic field that could strip the data off a credit card from as far away as the moon, or distort the very atoms in your body at a similar distance. In the vicinity of a magnetar, normal electromagnetic forces we are used to are completely overwhelmed by the star's intense magnetism. This magnetic power does not remain quiet. The magnetic field of a magnetar is intertwined with its solid crust. As the magnetar gradually cools and its magnetic field shifts over time, stress builds up in the rigid crust. Imagine the enormous tension of a magnetic field trying to realign itself through a solid layer of ultra-dense matter. Eventually, something must give. The crust can suddenly crack in what might be called a starquake. When this happens, in an instant, the pent-up magnetic energy is unleashed, producing a ferocious burst of radiation. For a brief moment, the magnetar erupts. From its surface, a flood of high-energy photons, X-rays and gamma rays, bursts forth, racing into space. These magnetar flares are among the most violent events known in the universe, short of a supernova. And yet, they come from something no larger than a city. In that moment of eruption, the magnetar can outshine entire galaxies in X-ray light. To our scientific instruments, it's like a sudden beacon blazing from across the cosmos, then fading away over mere seconds. One famous example of such an event took place on December 27th, 2004. Without warning, a magnetar on the other side of our galaxy let loose an enormous flare. In 1/10 of a second, it released more energy than our sun emits in 100,000 years. Even from a distance of tens of thousands of light years, the burst was detected by satellites and observatories here on Earth. It briefly ionized Earth's upper atmosphere, subtly affecting our planet from across a vast gulf of space. Had that magnetar been much closer, the effects on Earth would have been far more than a slight disturbance. It could have been catastrophic. Fortunately, these magnetic beacons are rare and usually very distant. In the aftermath of such a flare, the magnetar quiets down again. The starquake resolves, and the crust settles into a new shape, the magnetic field perhaps slightly reconfigured. The magnetar returns to its more usual state, a slowly spinning, highly magnetized orb, maybe emitting a steady glow of X-rays as it cools, or occasional smaller bursts of activity. But the memory of that burst, the incredible power released, lingers in the surroundings. Sometimes the area around the magnetar is filled with swirling clouds of plasma, charged particles, that were hurled out during the flare, caught in the magnetic field lines that loop out into space and back to the star. These glowing, eerie auroras around the magnetar gradually fade as the material drifts away. Magnetars rotate more slowly than some of their neutron star cousins. While pulsars can spin hundreds of times a second, a magnetar might take several seconds to complete one rotation. But what they lack in speed, they make up for in sheer magnetic might. It's believed that magnetars might be born when a particular combination of mass, rotation, and other conditions in a supernova create an especially powerful dynamo effect as the star's core collapses. In those first moments of a magnetar's life, its magnetic field is wound up to incredible strength. Over time, perhaps tens of thousands of years, the field may gradually weaken, and the magnetar might settle into a more typical neutron star life. But during that period of youth, the magnetar is a restless powerhouse. To put their might into perspective, if a magnetar were at the distance of the Moon from Earth, its magnetic field could erase every credit card on the planet and scramble the circuitry of our electronics. Closer still, within a few thousand kilometers, the magnetic forces could distort atoms and tear molecules apart. These objects are not friendly to close visitors. Fortunately, no magnetar lies anywhere near our solar system, and even the magnetar itself will not remain so volatile forever. Its fierce magnetic field is expected to gradually wane over tens of thousands of years. As the field weakens, the magnetar will calm, eventually behaving more like a typical neutron star or pulsar. In a sense, magnetars live fast and intense in their youth, then mellow with age, no longer prone to the massive flares that made them so dramatic. From a distance, if one could watch a magnetar safely, it might not look very different from other neutron stars until it flares. Perhaps you would see a faint X-ray glow. But if you had instruments to measure magnetic fields, you would notice an enormous bubble of magnetism around it, influencing charged particles in its vicinity. Were you foolish enough to approach, your spacecraft's electronics would fail long before you got close, scrambled by the intense magnetic environment. Magnetars are comparatively rare. Only a few dozen have been confirmed among the millions of stars in our galaxy. They tend to announce themselves through those dramatic outbursts or as unusually bright, fluctuating X-ray sources. When not flaring, magnetars can also emit steady pulses of high-energy radiation, and some are detected as pulsars, their strong magnetic fields, funnel beams of particles and light that pulse as they rotate. Yet their pulse patterns might be erratic or slower than typical pulsars, revealing that something different is happening under the surface. In the grand stillness of space, a magnetar's outburst is a stark reminder that even in the apparent calm, tremendous forces can be unleashed in a heartbeat. Imagine floating in the dark near a silent neutron star, and suddenly, a crack like thunder, not heard as sound, but felt as a surge of energy, rips through the fabric of space around you. A flash of light brighter than anything you've seen, if your eyes could perceive gamma rays, erupts, and then all returns to quiet darkness. The neutron star continues on as if nothing happened, but you have witnessed one of the universe's most powerful fireworks. The magnetic titans challenge our understanding of physics. In their magnetic fields, vacuum itself behaves in unusual ways. Light can become polarized and split in a phenomenon called vacuum birefringence, as though even empty space is influenced by the magnetism. Such exotic effects have been hinted at in observations, offering a testing ground for quantum physics under extreme conditions. As we observe magnetars from afar, we learn not only about these strange stars, but also about the fundamental forces at play. They show us the extremes of magnetic energy and how it can warp and shatter matter in an instant. They also remind us of the resilience of these neutron stars. Even after a colossal flare that shakes the star to its core, the magnetar remains intact, a cracked but unbroken sphere of neutrons, spinning gradually in the silent night. The existence of magnetars paints yet another facet onto our picture of neutron stars. Not only are they incredibly dense and gravitationally intense, but they can also be magnetic gods, wielding fields so powerful that the usual rules of electromagnetism bend under their influence. And yet, for all their might, to the casual gaze of a human with an optical telescope, they would appear as unremarkable points of light or be invisible altogether. Their fury and power are hidden in the invisible spectrums of X-rays and gamma rays and in the invisible lines of magnetic force. Through magnetars, we see nature's capacity for extremes. They are a cosmic paradox. On one hand, they are quiet, dark stellar remnants drifting in space. On the other, they are capable of unleashing sudden ferocity that can be detected across the universe. In the continuing journey to understand neutron stars, magnetars stand out as the most magnetic, unpredictable characters, the true titans of magnetism among the stars. Among the neutron stars drifting through the galaxy, many are effectively invisible, but some take on a remarkable role as cosmic beacons. These are the pulsars, neutron stars that send out beams of radio waves, and sometimes X-rays, or even visible light, with astonishing regularity. They spin like celestial lighthouses, and each time their beam sweeps past Earth, we detect a pulse of emission, like a distant beacon flashing rhythmically in the night. Picture a dark landscape by the sea, where a lighthouse turns its light in circles. To a distant observer, that lighthouse isn't constantly visible. Instead, they see a flash each time the light's rotation brings it into view. Similarly, a pulsar emits a focused beam along its magnetic poles. If those poles are oriented just right, the beam crosses our line of sight once every rotation. What we observe is a steady pattern of blinks, on and off, with a precision that can be astounding. The star itself is shining constantly, but we only see the light when it's pointing our way. The first time humans detected such a signal, it was so regular that it defied immediate explanation. The pulses arrived every 1.3 seconds, like clockwork. The discoverers, surprised by the precision, even humorously dubbed the source LGM1 for Little Green Men 1, half-jokingly considering that it might be a signal from an intelligent civilization. It was quickly realized, however, that this was no alien beacon, but a new kind of star, a rapidly spinning neutron star sending out lighthouse-like beams. Thus, pulsars were discovered, revealing the presence of neutron stars through their rhythmic signals. Pulsars can spin at very different rates. Some rotate a few times per second, sending out leisurely, spaced-out pulses. Others spin incredibly fast, hundreds of rotations each second, their pulses coming in a rapid-fire beat, more like a hum than a click. Imagine a sphere the size of a city, spinning hundreds of times every second. At its equator, the surface moves at a significant fraction of the speed of light with each rotation. These fast pulsars, called millisecond pulsars, complete a rotation in the blink of an eye, just a few thousandths of a second. Their beams flicker so rapidly that if we converted their radio signals to sound, we'd hear a very high-pitched whir or tone. In fact, the fastest pulsars known spin close to 700 times a second. That's over 40,000 revolutions per minute. At that rate, the neutron star's equator moves at roughly a fifth of the speed of light. This is nearly the limit of how fast such an object can spin without breaking apart under its own stress. It's astonishing to imagine an entire star, even a small one, spinning so rapidly and yet so steadily. Despite these blistering speeds, pulsars are incredibly steady rotators. The most stable ones keep time more accurately than the best mechanical clocks. Indeed, some rival atomic clocks in precision. Over years, their ticks only very slowly change, typically slowing as they lose energy. Some pulsars occasionally glitch, a sudden tiny increase in spin rate, which scientists believe may be due to adjustments in their superfluid interiors or quakes in their crust. But aside from these small surprises, a pulsar's beat is a dependable cosmic metronome. This steadiness is useful. Astronomers use pulsars as tools to probe space and time. By measuring slight variations in the timing of pulsar signals, researchers can detect things like intervening clouds of interstellar gas, or the subtle gravitational tug of orbiting planets around the pulsar. In fact, the first planets ever discovered outside our solar system were found orbiting a pulsar. It was an unexpected place to find planets, circling a small, dead star and bathed in intense radiation. These pulsar planets are unlikely homes for life, but their discovery showed the ingenuity of nature in placing planets, even around such exotic suns. To a listener tuned to the cosmos, a single pulsar might sound like a rhythmic beat, pulsing steadily, patiently, across thousands of light years. Multiple pulsars together create a kind of cosmic symphony of different beats, some slow and deep, others rapid and high. It's almost as if each pulsar has its own tempo, set by its rotation, contributing a unique pattern to the galaxy's background music. Some pulsars are also sources of visible light, though faint. A famous example is the pulsar in the heart of the Crab Nebula, a supernova remnant. That pulsar spins about 30 times a second. It's so energetic that it actually pulses in visible light and X-rays. Through a telescope, one can see the star flickering dozens of times a second at the center of that swirling nebula, a tiny flashing beacon amid the glowing gas, faithfully ticking away since the explosion that created it was witnessed on Earth nearly 1,000 years ago. Pulsars also have strong magnetic fields, though typically not as extreme as magnetars. These magnetic fields channel particles into jets at the magnetic poles, which generate the radiation beams. As the pulsar spins, it gradually loses energy, slowing down over millennia, and its pulses grow slightly farther apart. Eventually, after millions of years, a pulsar may slow and dim to the point where it no longer emits detectable pulses, becoming a more quiescent neutron star. But while they are active, pulsars are among the most useful beacons nature has provided. Scientists have even imagined using pulsars as a kind of GPS in space. Because their positions in the galaxy are fixed and their pulses are so regular, a spacecraft with the right instruments could, in theory, measure the arrival of pulses from several known pulsars and triangulate its own location, much like we use GPS satellites. In fact, embedded on the Voyager spacecraft plaques that were sent out of the solar system is a map of pulsar positions and pulse frequencies, a cosmic address telling any finder of Voyager where it came from, using pulsars as the guide points. Not all pulsars exist in solitude. Some have companions, either ordinary stars or other neutron stars, in orbit around them. In these binary systems, the pulsar's gravity can pull matter from a companion star, creating a hot accretion disk of material that funnels onto the neutron star's poles, often producing intense X-ray emissions. These are known as X-ray pulsars, as they flash in X-ray rather than radio, fueled by the fresh infalling material. If the infalling matter also adds angular momentum to the neutron star, it can spin the pulsar up, making an old pulsar young again in a sense, and increasing its rotation rate to become one of those millisecond pulsars. These spun-up pulsars are sometimes called recycled pulsars, revived by the transfer of mass and momentum from a companion. In rare cases, pulsars are found with another neutron star, or even a black hole, as a partner. These binary pulsar systems are laboratories for extreme physics. As they orbit each other, Their immense gravity causes the fabric of space-time around them to wobble and ripple. The pulsar's clock-like pulses allow astronomers to measure these motions with exquisite precision. Over time, we can observe that the orbit is shrinking ever so slightly as energy is carried away by gravitational waves, subtle ripples in space-time predicted by Einstein. Decades ago, observations of a binary pulsar provided the first indirect evidence for the existence of gravitational waves. Because the pulsar and its neutron star companion were spiraling together at exactly the rate general relativity predicted due to energy loss by these waves. It was a stunning confirmation that even in the realm of these tiny, dense stars, the grand cosmic dance is governed by the laws of gravity. The pulsar's rhythmic flashing, therefore, not only marks the passage of time, but also encodes stories of its environment, from asteroids or planets tugging at it to entire stars dancing in tandem. Each slight irregularity in the beat can reveal a new discovery. If you could sit back and watch the galaxy in radio waves, you would see thousands of little blinking lights, the pulsars scattered throughout the Milky Way. Most are too faint to notice, but a few stand out with fast, bright pulses. They sweep around steadily, unnoticed by human senses, but faithfully broadcasting their existence. Indeed, astronomers have catalogued over 2,000 pulsars across the Milky Way, each a rotating monument to a long-dead star. Like cosmic lighthouses, they silently keep vigil in the darkness, each pulse a testimony that a tiny, dense star is there, spinning with sublime regularity. It's a comforting thought in a way. Even in the vast, chaotic processes of the universe, these neutron stars provide a heartbeat, a steady ticking rhythm amid the cosmic silence. As we follow these pulsing beacons, they guide us naturally toward the next mystery. Some pulsars, as mentioned, share their lives with companions, swirling in tight orbits. What happens if two neutron stars, each perhaps a pulsar in its own right, continue their spiral toward each other? The answer lies in the very fabric of space and time, an answer that comes in the form of gravitational waves and sometimes in the spectacular finale of a neutron star collision. Not every neutron star is a flamboyant beacon or a magnetic powerhouse. Many live out their existence in quiet obscurity, drifting through the galaxy as dark, silent wanderers. These solitary neutron stars, without a companion to feed them, or the particular alignment to beam pulses toward us, are nearly invisible against the blackness of space. They are like cosmic ghosts, the remnants of stars that roam the interstellar night with hardly a trace. Set adrift by their violent births, these stellar remnants can travel at incredible speeds. In some cases, the supernova explosion gives the newborn neutron star a powerful kick, propelling it through the galaxy at hundreds of kilometers per second. Over millennia, a neutron star can migrate far from its birthplace, becoming a cosmic vagabond with no fixed home, carrying on with the momentum imparted to it by its mother star's final blast. Imagine one such neutron star moving silently through the void between stars. From a distance, it emits no noticeable light. Its once fiery birth is far behind it. The supernova remnant that may have glowed around it has long since dissipated into the galactic medium. Now it's just a bare, dense core traveling on its own. If you were to encounter it, you might not realize it's there until you felt its gravity tug at your spaceship, or noticed how it bends the starlight from objects behind it, acting as a subtle gravitational lens. In the emptiness of space, this lonely remnant is practically a black sphere, perhaps with a faint surface temperature of 100,000 degrees, extremely hot by everyday standards, but so small that it radiates only weakly. With no ongoing energy source, it has been cooling since the day it was born. In its youth, it may have glowed with X-rays, but now, after millions of years, that glow has faded. The neutron star is still warmer than the space around it, but not by enough to stand out unless you look very closely with sensitive instruments. As it drifts, it may occasionally wander through thin clouds of interstellar gas. When it does, its gravity draws in some of that gas, which can heat up and emit a bit of X-ray light as it spirals in, revealing the neutron star's presence. Such events are rare and subtle, like a whisper in the darkness. For the most part, an isolated neutron star can travel undetected. There could be tens of millions of these stellar remnants scattered throughout our galaxy, and we have identified only a small fraction. They are so inconspicuous that only their gravity betrays them, perhaps by a slight pull on visible objects, or by bending the path of light from a background star in a fleeting gravitational lensing event. These quiet wanderers carry the story of their long journey. Without companions or strong magnetic emissions, they simply persist. Over the eons, they slow their rotation very gradually, as even the faintest of electromagnetic winds from them carry away energy. A neutron star that might have once spun multiple times per second could, after tens of millions of years, rotate just once every few seconds or slower, gradually losing the exuberance of youth. But it remains a neutron star, and unless it collides with something or gains new material, it will remain one indefinitely. What would it be like to approach such an object? Picture yourself far out in interstellar space, with no stars brightly visible nearby. You could float right past a solitary neutron star, and without instruments, you might not notice anything unusual. There's no light, no sound, just an invisible gravitational presence. But if you looked at the field of stars behind it as you flew by, you might notice them warping and shifting slightly, as if seen through a faint lens. This is the neutron star's gravity bending their light, a subtle optical illusion in the sky. If you moved even closer, ignoring the fatal gravity for this thought experiment, you might see a faint halo of light around it, the distortion of the background starlight wrapping around the neutron star, making it appear ringed by a thin band of light. This gravitational lens effect would be one of the few giveaways that something massive and compact lurks in the dark. It's poetic in a way. A star that once shone brightly, lived a full life, died in a cataclysm of light, and now in its afterlife, it travels unseen, affecting its surroundings only through the force of its gravity. These neutron stars are stellar remnants stripped down to just mass and gravity. No shining fusion fire, no dramatic flares, just the heavy weight of their existence moving through space. Occasionally, astronomers have caught glimpses of such isolated neutron stars. A handful have been detected as faint X-ray sources with no accompanying star or nebula, just a lone point of X-rays slowly moving across the sky. These are sometimes nicknamed the Magnificent Seven, a small group of nearby isolated neutron stars identified by their faint, soft X-ray glow. They are likely relatively young, a few million years old, and still cooling. Even these are hard to observe. They don't pulse brightly or erupt. They merely shine feebly as they release the last of their heat. By studying them, scientists can learn about the cooling process of neutron stars and the states of matter in their crusts and cores. Each one is like a tiny laboratory of extreme physics hidden in plain sight. For the most ancient neutron stars, billions of years old, even that residual heat might have radiated away to the point where they are truly dark. Cold, solid neutron star husks drifting endlessly. The universe is not yet old enough for any neutron star to have fully cooled to absolute darkness. Even the oldest have a bit of warmth left. But trillions of years in the future, long after our sun has died, these neutron stars will still be around, having gradually become colder and fainter, effectively invisible, yet still as massive and dense as ever. They will be like silent memorials of stars that once were, indestructible, except by the rare chance of a collision, or by collapsing into a black hole if they somehow gather extra mass. These hidden wanderers add a note of mystery to our galaxy. We suspect there are many more neutron stars around us than we can currently find. They could be passing silently through the outskirts of our solar system, or among the nearby stars. And we might not know, unless we stumbled upon one by its gravitational pull. The idea that these ultra-dense spheres are out there, unseen in the darkness, can be both eerie and fascinating. They remind us that the cosmos holds secrets. Not everything bright is all there is. Some treasures of the universe hide in the dark, only indirectly revealing themselves. In the stillness of space, a solitary neutron star does not announce itself with light or sound. It simply moves according to gravity's command, an obedient wanderer, following the momentum imparted to it by the supernova that set it free. Each such object will continue its silent voyage until perhaps one day fate intervenes. Maybe another star's gravity will capture it, or it will join a stellar system, or in an immensely distant future, two lonely neutron stars might chance upon each other and merge. But until such an encounter, they remain alone. Though quiet and unassuming, these hidden neutron stars are an important part of the galactic ecosystem. Over billions of years, they might occasionally play a role. For instance, if one passes through a dense molecular cloud, it could trigger some compression that leads to new star formation. Or if one drifts near a planetary system, its gravity could perturb comet clouds at the fringes. Such interactions are subtle and rare, but they illustrate that even in solitude, a neutron star's gravity can have influence. For us, the hidden wanderers are a reminder of how much is out there, unseen. As our instruments improve, we may discover more of them, turning the invisible into the observable. But even without seeing them directly, we know they roam the galaxy like silent ships on a dark cosmic sea, each one a relic of a stellar life, now quietly continuing on an endless journey. Throughout our journey, one thread has been woven through every aspect of neutron stars: gravity. It is gravity that forced a star's core to collapse into a neutron star in the first place. It is gravity that holds the neutron star together against all odds, and gravity that choreographs the motions of these stellar remnants through space. Around a neutron star, gravity is so intense that it shapes the very fabric of reality. Space is curved sharply, and time itself flows differently. If you could venture close to a neutron star, you would find that time around it is subtly warped. An observer far away might see your movements near the neutron star as strangely slow, like a film playing in slight slow motion. Conversely, if you were the one near the neutron star, you might look out and see the universe beyond running a bit fast. This effect, known as gravitational time dilation, means that clocks tick more slowly in stronger gravity. On the surface of a neutron star, the pull of gravity is so great that time can slow significantly compared to Earth. For example, roughly speaking, 8 years might pass for someone standing on a neutron star, if that were possible, while 10 years pass for someone far away. This isn't science fiction. It's a consequence of Einstein's theory of general relativity and has been measured in less extreme conditions, like around Earth and the Sun. Near a neutron star, the warping of time and space is intense, though not as absolute as around a black hole. Space around a neutron star is also curved strongly. We've already imagined how light can bend around a neutron star, letting you glimpse areas behind it. In a sense, a neutron star carries a dent in the fabric of space-time. Anything that comes too close will find its path forever altered, drawn in by this curvature. Even beams of light find themselves detouring, curving inward as they pass by. If the neutron star is compact and massive enough, it could even trap light in orbit briefly. All these strange effects, time dilation, light bending, are the universe's way of communicating the presence of a massive, compact object. It's as if gravity is the language a neutron star uses to make itself known, especially when it otherwise emits little light. But neutron stars have an even more dramatic way to speak through gravity. When they move, especially in pairs, they can send gravitational waves rippling through space. Gravitational waves are literally vibrations in space-time itself, spreading outward like ripples on a pond after a stone is dropped. When you have two massive objects like neutron stars orbiting one another, their gravity stirs the space-time around them, creating these ripples that carry energy away at the speed of light. Consider a pair of neutron stars bound together, perhaps the remnants of a binary star system that both went supernova. They orbit each other in a wild dance, maybe starting at a respectable distance apart. Over time, millions or billions of years, this dance tightens. As they orbit, gravitational waves carry away tiny amounts of their orbital energy, causing the neutron stars to spiral gradually closer. For eons, these waves would be very weak, far too faint for us to notice from across the galaxy. But as the neutron stars draw nearer, the waves grow stronger. The dance speeds up. What might have been an orbit taking hours shrinks to minutes, then to mere seconds. In their final moments, the two neutron stars whirl around each other dozens, then hundreds of times per second, closing the gap between them inexorably. During those last few seconds, the gravitational waves sent out by the neutron star pair rise to a crescendo. If one could somehow hear gravitational waves, one would perceive a kind of rising tone, a chirp, as the frequency and amplitude increase. Space itself is ringing with the energy of their motion. These waves carry the news of the impending merger across the cosmos. Then, finally, the two neutron stars meet. In a fraction of a second, they collide. What happens in that exact instant is extraordinary. The neutron-rich matter of both stars crashes together at a significant fraction of the speed of light. Temperatures reach levels rivaling those of a supernova, and densities momentarily might exceed even the normal density of a neutron star. The collision may result in a combined object. For a short time, a hypermassive neutron star, which likely then collapses quickly into a black hole under its own weight. Alternatively, if enough energy is flung out, the remnant might remain a very massive neutron star. Either way, a tremendous amount of matter is ejected in the collision. This ejector, ripped from the neutron stars, is rich in heavy elements and radioactive isotopes, freshly forged in the incredible neutron bombardment of the merger. In that moment of collision, two forms of cosmic fury are released: gravitational and electromagnetic. The gravitational waves surge as the two objects become one, then suddenly fall silent beyond the merger. The final chord of their gravitational song has been played, echoing outwards. At the same time, there is a flash of electromagnetic energy. Often, The merging of neutron stars powers a short but intense gamma ray burst, a focused blast of gamma rays that can be observed across the universe. Such a burst lasts only a second or two, but for that brief moment, it can outshine almost all other gamma ray sources in the sky. Following this, the cloud of ejected material, the debris from the collision, begins to shine. This is the kilonova, a thermal afterglow from the radioactive decay of those freshly minted elements. Initially, it may glow a bluish color as the hottest, lightest elements radiate. Then it shifts to red as heavier elements dominate and the cloud expands and cools. To telescopes, it appears as a new pinprick of light in a galaxy, one that fades over days and weeks. This kilonova is relatively dim compared to a typical supernova, but it's rich with heavy elements. In those few days of existence, this transient object produces huge quantities of gold, platinum, uranium, and many other heavy elements, synthesizing what normal stars alone cannot. Such an event is truly the light and fury of the cosmos condensed. Light in the sense of electromagnetic radiation across the spectrum, and fury in the sense of unimaginable energies and the violent upheaval of the merger. For a long time, these collisions were purely theoretical to us. But recently, humanity witnessed one in both gravitational waves and light. In one remarkable case, astronomers around the world heard the approaching whispers of gravitational waves from two neutron stars spiraling together. Our detectors on Earth gently shook as the space-time ripples passed through, faithfully recording the final minute of the neutron stars in spiral. Then, just seconds after the gravitational wave signal ceased, signaling the merger had occurred, space telescopes caught a burst of gamma rays from a distant galaxy. Within hours, observatories had pinpointed a new, bright point of light in that galaxy, the kilonova created by the merger's debris. We had, for the first time, both heard and seen the collision of neutron stars across millions of light years. It was as though we suddenly gained not just sight, but a new sense, hearing, in the cosmos, confirming a story that had long been told by theory. This watershed observation confirmed that gravitational waves are a real messenger, a new way of experiencing the universe. It proved that yes, neutron star collisions are indeed responsible for short gamma-ray bursts, and that they do forge heavy elements. The spectra of the kilonova's light revealed signatures of exotic elements forming and decaying, exactly as predicted. It was a moment of sublime connection. An event in a galaxy far away sent tiny tremors through the fabric of space that we felt under our feet, and at the same time sent photons into our telescopes, allowing us to piece together a complete picture of what happened. As rare as such an event is, in any one galaxy, perhaps only once in 100,000 years, the universe has hundreds of billions of galaxies. So, somewhere in the cosmos, nearly every day, neutron stars are colliding and sending out their final cries of light and gravity. Each one enriches its corner of the universe with new elements, contributing to the grand cycle of cosmic evolution and renewal. Think about the journey of those gravitational waves and that light. For over 100 million years, in the case of the observed event, two neutron stars orbited each other in silence. In their final moments, they cried out in the language of gravity, sending ripples through space itself. Those ripples traveled across the void, crossing intergalactic distances, weakening with expansion, but never faltering in their message. Meanwhile, the light from the collision followed, a bit slower to arrive since it was emitted slightly after the gravitational waves. When those signals reached Earth, humans had only just developed the sensitivity to catch them. We happened to be listening at the right moment. By capturing these faint murmurs and flashes, we extended our senses across the universe. What's profoundly moving is how these cosmic events tie into our own existence. The gold in a ring on someone's finger, the iodine in our bodies, the uranium in the rocks beneath us. These and many other elements owe their origin to the furious alchemy of neutron star collisions. The death of two stars in a distant past can provide the material for planets and life in the future. In a very literal way, we are connected to these dramatic events. Our world contains atoms, forged when neutron stars merged. Atoms scattered through space that eventually coalesced into the Earth and even into us. Every heavy element around us is a souvenir of cosmic violence, turned into something beautiful and useful. As we come to the end of our journey among neutron stars, we can reflect on the grand tapestry they are part of. We saw a massive star's core collapse into a tiny ember, a neutron star born from a supernova's ashes. We marveled at the density and structure of that ember, at magnetars that crackle with energy, and pulsars that beat like cosmic hearts in the darkness. We imagined the silent, lonely ones drifting invisibly. And finally, we witnessed the dramatic dance of gravity that can bring two neutron stars together in a final embrace, releasing both the fierce burst of a kilonova and the gentle whisper of gravitational waves. Despite their small size, neutron stars have a vast influence on our understanding of physics and the cosmos. They push matter to its limits, produce staggering magnetic fields, serve as lighthouses and laboratories, and even in their explosive unions, they sow the seeds of new worlds. They exemplify a theme that recurs throughout the universe. From great destruction comes new creation. A star dies, and a neutron star is born. Two neutron stars collide, and new elements are forged, spreading into space to become part of new stars and planets. In the face of such cosmic enormity, one might wonder about the significance of our own lives. Yet, here lies a comforting truth. We are connected to these stars. The calcium in our bones, the iron in our blood, the gold adorning our world, they were forged in stellar furnaces and cosmic collisions. We are quite literally made of star stuff. In this way, the universe is within us, and we are a part of the universe. Knowing that the violent death of stars can lead to the ingredients of life offers a kind of solace. It means that even the fiercest cosmic events contribute to the creation of something new, including us. We are the universe's observers, born from its fires, and now able to reflect on it. This realization can bring a peaceful sense of belonging and purpose. The chaos of supernovae and neutron star collisions ultimately enabled the calm of our night sky and the life beneath it. Out of cosmic fury came the possibility for awareness and wonder. There is harmony in that perspective, a reassurance that even in destruction, nature is crafting the foundation for new beginnings. It reminds us that we are part of something vast and magnificent. Now, as we conclude our journey, let the image of these distant neutron stars settle gently in your mind. Tiny, massive, powerful, gentle, destructive, creative, all at once. In their existence, they tie together birth and death, chaos and order, violence and beauty. They truly are light and fury in the cosmos, and yet listening to their story can bring a strange peace, a perspective that in the grand scheme of things, even the most cataclysmic events lead to renewal and wonder. Allow yourself to feel the scale of it, yet also the comfort that we reside in a quiet corner of this grand stage, able to observe and reflect. The neutron stars continue their cosmic ballet, whether or not anyone watches. But knowing about it enriches our experience of the night. It reminds us that even in darkness, the universe is alive with events. The slow dance of gravity, the silent melody of stars ending and beginning. Perhaps tonight, as you drift to sleep under the same familiar sky, a neutron star somewhere is being born in a brilliant supernova, while another, somewhere else, is quaking with magnetic fury. Perhaps two others are circling closer and closer, getting ready to merge and fling their gift of heavy elements into the galaxy. These events will happen heedless of our presence, grand cosmic rhythms playing out far beyond. Yet we have the privilege to witness some of them from afar, to study and to marvel. In the end, neutron stars are both destroyers and creators, quiet loners and vigorous beacons. They encapsulate extremes beyond ordinary experience, yet they are fundamental to the story of the universe. They are, in a sense, the cosmos, contemplating its own extremes, places where matter, energy, space, and time do things they rarely do elsewhere. And they speak to us through pulses of light or ripples in space-time, telling us their tale if we listen. Our exploration of these cosmic wonders leaves us with a sense of awe and serenity. The next time you look up at a peaceful night sky, remember that far beyond the gentle twinkle of the stars, the universe is alive with the light and fury of events like neutron star collisions, pulsar beacons, and magnetar flares. Even when all seems still, there is motion and music in the darkness, the slow dance of gravity, the silent hymn of creation and destruction. With that awareness, we can find both wonder and calm. We recognize that we are in the midst of a grand cosmos that is fierce and beautiful, and that somehow we are a part of it. As the cosmic stage dims in our mind's eye, the neutron stars, our protagonists, fade back into the obscurity of space. Their influence, however, remains everywhere, in the gravity that binds galaxies, in the elements that build worlds, and in the inspiration they give us to keep exploring. The tale of neutron stars is but one chapter in the universe's story, one that will continue to unfold for eons to come. As we gently return from this voyage across space and time, we carry with us a piece of that cosmic mystery and serenity, a quiet reminder of the incredible events playing out beyond our sight, as steady and as subtle as our own heartbeat in the dark. For some neutron stars, the end of their life as a normal star is not a solitary affair. In the quiet darkness of space, there are pairs of these stars locked together, continuing their story side by side. Bound by gravity, two neutron stars orbit each other in a tight, relentless dance. They circle around a common point, swinging closer and then farther apart, repeating their cosmic steps over and over in the void. Each star is incredibly dense, containing more mass than our sun crushed into a sphere only a few miles across. As they spin around one another, their gravity grips each partner firmly. The curvature of space around them is intense, and their mutual pull keeps them tied together. In this cosmic dance, they are like two ice skaters clasping hands, spinning faster as they draw nearer. There is a beauty in their motion, but also a silent tension that foretells a coming change. All other remnants of their former lives, any planets or gas, have long since been swept away or consumed, leaving just these two dancers alone in the darkness. In this binary waltz, time moves slowly yet surely toward an inevitable finale. For now, these two dark stellar remnants glide through their orbits, perhaps completing one loop in just a few hours. If someone could watch from a safe distance, they would see two faint points circling each other at astonishing speeds. The stars might be invisible to the eye, but one could make itself known as a pulsar, sending regular flashes of radio waves as it spins. Those flashes would rise and fall in frequency as the star moves toward us or away, revealing the details of its orbit with each passing cycle. Each tick of that pulsar would be like a cosmic heartbeat, echoing the orbital rhythm and subtly changing as the dance speeds up. Long ago, these neutron stars might have lived very different lives as giant suns shining in the galaxy. They may have been born as a pair, two bright siblings burning nuclear fuel in tandem. Each met its end in a supernova explosion, collapsing into an ultra-dense core. Against the odds, both survived that chaos and remained gravitationally bound to each other. Now, all that's left of those once mighty stars are these two city-sized spheres of degenerate matter. They carry on around each other in a celestial circuit, the aftermath of violence settling into an eerie, stable rhythm. To picture their scale, each star is only about 20 kilometers across, a city-sized sphere, yet weighs more than our sun. The gravity near their surface is so intense that if anything stray ventured too close, it would be torn apart or pulled in. But this stability is only temporary on cosmic timescales. Every orbit is a prelude to their fate. With each pass, something imperceptible is happening. The dance is changing. The stars draw infinitesimally closer together as time goes on. There is no outside force pushing them, no collision with other objects. Instead, the change comes from the dance itself. Slowly, steadily, the energy of their orbital motion is leaking away into the cosmos. The two partners are on a path that leads inward, a path set by nature's fundamental forces. Their dance, though graceful, is a doomed one. In fact, astronomers on Earth have measured this slow decay in certain binary pulsar systems, watching as each orbit takes a few moments less than the last over many years. A gentle confirmation that the spiral inward is truly happening. These neutron stars are caught in orbits of doom. It is a slow doom, one that will take perhaps millions or even billions of years to unfold. For ages, they complete circle after circle, unharmed, seemingly eternal. Nothing visible signals their approaching destiny. Yet, inevitably, they spiral ever so slightly toward each other. It's a fate sealed by the same gravity that binds them. The invisible grip that holds them together is also drawing them in. In the emptiness around them, a silent announcement is being made with each orbit, a whisper of energy leaving the system, heralding what is to come. In the depths of space, no one can hear sound, but if we could somehow listen to the fabric of space-time itself, we would detect a faint sigh each time these stars orbit. This gentle sigh carries away a bit of the system's life. The process is so slow that to any observer, the stars seem to trace the same path over and over without change. But across millennia, their separation shrinks step by step. The dance quickens almost imperceptibly, as if the music of the cosmos is playing a crescendo that only the universe can hear. It's akin to a barely audible bass note gradually sliding up the scale, a cosmic lullaby accelerating toward a climax only the universe can hear. There is a precarious balance in this dance. Each neutron star moves in a curved path dictated by gravity, always trying to fling outward, yet always being pulled back by its companion's mass. If one could trace their motion, it would look like a pair of endless ellipses locked together. As long as nothing disturbs them, they would continue circling each other like this. Yet, the very act of orbiting is sowing the seeds of their end. In a universe governed by Einstein's general relativity, moving masses can create disturbances in spacetime. And here, two massive objects in motion are doing just that, sending subtle ripples through the cosmos as they twirl. Those ripples carry away energy from the system. It is an incredibly slow bleed, far too slow to notice in a single human lifetime. But it is steady. The neutron stars have no choice but to gradually draw closer as their orbit loses this energy. They are destined to meet, though the journey toward that meeting is long and uneventful for eons. The concept might seem strange. How can simply orbiting each other cause them to inch closer? The answer lies in those invisible waves, the gravitational waves that spread outward from the binary. This gentle radiation of space itself is the herald of their doom, an announcement sent out in all directions that these two stars are spiraling in. Far across the galaxy, perhaps on some distant world, the faint echoes of that dance might eventually pass by. These ripples are incredibly weak by the time they travel light years away. They stretch and squeeze the fabric of space so subtly that nearly everything ignores them. But they carry the signature of the two orbiting stars, like a broadcast of the dance. In the vast emptiness, these signals fade almost into nothingness. Yet they continue traveling onward, carrying news of what's happening in this hidden corner of the cosmos. Thus, two neutron stars continue their precarious dance. In cosmic solitude they twirl, bound by gravity's unyielding hold. Each revolution brings them an infinitesimal step closer to their fate. Unseen and unfelt by anyone, they are slowly winding down like a clock. At this moment they are still separate, two distinct points locked in orbit. But the stage is being set for a dramatic future. One day, far, far in the future, their orbits will become so tight that nothing can keep them apart. One day, the dance will end in a final embrace, unleashing forces unlike anything else in the universe. In time, when that final moment comes, they will transform violently, an event that will send ripples and light across the cosmos. Albert Einstein first described these space-time ripples over a century ago. According to his theory, whenever massive objects accelerate, like two stars orbiting each other, they should create waves in the very fabric of space and time. These gravitational waves spread outward at the speed of light, carrying away a tiny amount of energy from the system. In most everyday cases, the effect is so vanishingly small that it is completely negligible. But in the dance of neutron stars, with their immense masses and tight orbits, gravitational waves become an important player. Initially, even Einstein himself wasn't certain these waves would be anything more than a mathematical curiosity, because they seemed impossibly weak. With each orbit, the neutron stars send a little more of their energy out into the universe in the form of these waves. It's as if every time they spin around, they give a slight, almost undetectable shudder that radiates away. This loss of energy means the stars have less to keep them moving apart, so gravity pulls them a bit closer. The orbit shrinks ever so slightly. At first, the change is incredibly slow, but it is steady. Over long periods of time, those tiny losses add up. Like a clock winding down, the binary system gradually loses orbital energy. The two stars are drawn closer together than they were before, their dance floor subtly contracting under their feet. Decades ago, astronomers found the first strong hints that this was really happening. In the 1970s, a pair of scientists discovered a special neutron star system, a pulsar circling another neutron star. By carefully timing the pulsar's radio blinks, they could map out its orbit with extreme precision. They noticed something remarkable. The interval of the orbit was getting shorter at a very slow but measurable rate. Year by year, the two neutron stars were circling each other slightly faster, indicating the orbit was shrinking. No other forces could account for this change. It matched exactly what Einstein's theory predicted if gravitational waves were carrying off energy. This was the first indirect proof that gravitational waves were not just theoretical. They were real, quietly stealing energy from the orbit of those stars. Even with that evidence, for a long time, gravitational waves remained elusive signals, far beyond our ability to sense directly. The ripples through space-time are extraordinarily gentle. By the time they reach us from typical cosmic sources, they cause movements in matter that are smaller than an atom's nucleus. Space itself stretches and squeezes by an almost inconceivably small amount. To detect such a minuscule effect, we would need instruments of incredible sensitivity. It is like trying to feel the faintest ripple from a pebble thrown into the ocean when you are standing on a distant shore. The challenge is immense, and for decades, humanity could only imagine hearing these cosmic whispers. In the mid-20th century, scientists built massive bar-shaped detectors in hopes of sensing these ripples, but with no success. It became clear that only with cutting-edge laser technology and meticulous engineering could humanity have any chance to listen in on the faint music of space-time. Yet the effect on the neutron stars themselves, while subtle over years, becomes dramatic as they draw nearer. Early in their life as a binary, the energy loss is small, and the stars continue to circle for millions of orbits almost undisturbed. But as their separation decreases, the gravitational pull grows stronger, and they orbit faster. When they move faster and closer, they stir up space-time more vigorously, sending out stronger waves. This in turn removes energy even more quickly, causing an even faster in-spiral. It's a runaway process. The closer the stars get, the more energy is carried away, and the faster they come together. It's like a dancer spinning faster and faster as they pull their arms in. Except here, the dancers are stars, and their arms are invisible waves of gravity. Imagine the neutron stars, gradually picking up speed, as if on a spiral slide. In their final thousands of years, what was once an almost undetectable drift inward becomes a more noticeable march. And in the last minutes of their lives as separate stars, the energy loss to gravitational waves becomes enormous. In those moments, the power being radiated as gravitational waves is astonishing, briefly exceeding the output of light from entire galaxies. All of that energy is drawn from their orbital motion. They whirl around each other furiously, and each turn flings out more ripples into space-time, draining yet more of the energy binding them apart. Through this mechanism, gravitational waves act like a cosmic braking system. The waves carry away angular momentum and energy, and the neutron stars respond by spiraling inward faster and faster. There is no physical surface or medium doing the braking, just the fundamental physics of space-time. It is as if empty space itself provides the resistance, though in reality space is simply transmitting the energy away in wave form. By the time the stars are nearly at the point of collision, they have lost a significant fraction of their initial orbital energy, all of it radiated away across the universe as gravitational waves. This inexorable process ensures that what started as a stable orbit will end in a violent merger. Throughout this slow decay, the two neutron stars remain oblivious to their fate. They simply follow the dictates of gravity, moving along their curved paths. Nothing changes about the stars themselves for most of this journey. They remain the same dense, cold remnants they have been since their formation. But unseen to them, a trail of gravitational energy fans out behind every orbit. If one could see these gravitational waves, it might look like concentric ripples expanding outwards, like the wake behind a boat, nearly imperceptible in the vast cosmic sea. These ripples travel onward indefinitely, carrying news of the impending merger long before it actually happens. In the final phase, just before merging, the gravitational wave emission reaches a crescendo. The once slow leakage of energy turns into a torrent. It happens so rapidly at the end that within the last second, the stars perform dozens of orbits, blurring together in a frantic spin. The gravitational waves now leaving the system are far stronger than any that came before, effectively broadcasting the final call of this doomed dance to the universe. When the stars finally coalesce, an immensely powerful burst of gravitational energy surges outward. That burst is the closing chord of their in-spiral, the last reverberation of their long spiral inward. In that tiny fraction of a second, the power unleashed exceeds that of 1 billion suns. For a brief moment, this merging system outshines entire galaxies in gravitational waves and high-energy light. For countless millennia, all of this transpired in silence and secrecy, unnoticed by any living thing. The only witnesses were the stars themselves and the fabric of spacetime. But those outward-bound ripples did not vanish. They travelled onward through the cosmos. Eventually, after journeying across unimaginable distances, some of these gravitational waves would reach places where intelligent life had built instruments to listen. The slow spiral inward sets the stage, but the story of these waves continues with their journey across space, and with their eventual detection by curious beings on a small blue planet. If we could see these gravitational waves with our eyes, the sight would be surreal. We might watch space itself stretching and compressing rhythmically, as if it were an endless, invisible ocean gently rising and falling. But even right next to the orbiting stars, these ripples would be almost imperceptible without sensitive instruments. It is only during the very final moments, as the waves grow ferociously strong, that the fabric of space contorts in noticeable ways before settling again after the merger. For years, the Earth lay still as these cosmic echoes washed over it, unnoticed and unfelt. But quietly, human ingenuity was preparing to detect them. In labs and observatories, scientists built giant L-shaped instruments, each arm kilometers long, designed to feel the tiniest stretching of space. These detectors were isolated from noise, suspended and shielded to filter out every tremor from the environment. They waited, listening to the silence with patience and hope, like ears pressed against the fabric of the cosmos. Inside those long tunnels, a laser beam was split and sent down each arm, bouncing off mirrors and returning to recombine. In the absence of gravitational waves, the two light beams would cancel out perfectly. If a wave passed through, one arm would stretch slightly and the other shrink, causing a tiny signal to emerge. These facilities, like the laser interferometer, Gravitational Wave Observatory, LIGO, were designed to detect a distortion in space smaller than the width of an atom. On September 14th, 2015, in the pre-dawn hours, that silence was finally broken. At 4:50 a.m. Eastern Time, a subtle vibration danced through the laser beams at LIGO's Livingston Observatory in Louisiana. Just 7 milliseconds later, a matching signal appeared in LIGO's Hanford detector in Washington state. It was incredibly subtle, but it had the telltale form scientists had hoped to see: a rapid rise in frequency and amplitude, the characteristic chirp of two massive objects merging. That faint blip marked the first direct detection of a gravitational wave. At first, the team was cautious, wondering if this tiny chirp could be an artifact of earthly noise. But its shape and simultaneous appearance in both detectors left little doubt. The signal perfectly matched what had been predicted for a massive merger event. It was the moment that confirmed a century-old theory and opened a new window onto the universe. The source, as scientists later determined, was the collision of two black holes nearly 1.3 billion light-years from Earth. That first detection was a triumph, but it was just the beginning. 2 years later, in late summer of 2017, the instruments detected another signal, and this one was different. It began as a soft rumble far below the range of human hearing, then rose steadily in pitch over nearly a minute and a half, an eternity in gravitational wave terms. The pattern of this wave hinted at lighter objects spiraling together, circling faster and faster until they merged. Scientists knew immediately that this was likely the long-awaited whisper from a neutron star collision. The signal, like a cosmic melody, grew louder and higher until it stopped, signifying the moment the two stars became one. This time, the gravitational wave detectors were not the only ones to catch wind of the event. About 2 seconds after the wave signal ended, a burst of high-energy light was recorded by a satellite orbiting Earth. It was a flash of gamma rays, short and powerful, coming from the same patch of sky. This was no coincidence. It was the electromagnetic echo of the very same cosmic collision. Within hours, observatories around the world swiveled to that region of sky, searching for a new point of light. Sure enough, they found a faint, glowing spot in a distant galaxy about 130 million light-years away. It was the afterglow of the neutron star merger, a cosmic fire that had been lit by the collision we had just heard via gravitational waves. For the first time in history, a single cosmic event was observed in both gravitational waves and light. The collision of two neutron stars sent vibrations through space that gently shook detectors on Earth. And at nearly the same moment, it lit up the darkness with a flash of gamma radiation, followed by a fading glow. Astronomers had long suspected neutron star crashes were responsible for mysterious gamma ray bursts seen in the sky. And now here was the confirmation. The faint echoes in the detectors and the flash in the sky were two sides of the same cosmic coin, each telling part of the story of that distant disaster. This was a watershed moment, the cosmic equivalent of suddenly hearing sound in a film we had only been able to see. For ages, we had watched the universe in silence. Now it had spoken, and we were listening. The event caused a stir of excitement and wonder in the scientific community and beyond. Here was direct confirmation that gravitational waves not only existed, but could be used to locate and study events that produce both invisible waves and visible light. People spoke of a new era of multi-messenger astronomy, meaning we could now combine gravitational wave messages with traditional light-based observations to learn more than ever about the universe. It was as if we had suddenly grown a new sense. After only seeing the cosmos for millennia, we could now hear it as well. The universe, once observed in silence, had revealed its sounds and proven that they carried meaningful tales across time and space. That neutron-star collision, detected on Earth through multiple channels, felt like listening to the cosmos speaking in a full sentence rather than a single word. The gravitational wave was the low, resonant tone, and the gamma-ray flash and subsequent glow were the bright, visible flourishes. Together, they painted a richer picture of what had happened in that far-off galaxy. It wasn't just a silent movie anymore. It was a scene with both image and sound. Those echoes across the cosmos arrived as gentle vibrations in our instruments and points of light in our telescopes, synchronized by the laws of physics that govern these cataclysmic events. Over the following years, detectors have captured dozens of gravitational wave signals, some from black holes merging in darkness, others from neutron stars, and even pairs of objects where one might be a neutron star and the other a black hole. Each detection is like hearing a new note in the cosmic symphony, each telling us something about the orchestra of extreme objects performing across the universe. These initial breakthroughs proved that we had truly opened a new window on the cosmos. No longer were we confined to only what telescopes could see. With gravitational waves, we could sense the invisible, the hidden mergers in distant galaxies that might leave little or no light. The collisions of neutron stars were no longer mere theoretical events lost in the vastness of space. They became real, observable occurrences that left echoes we could record and study. As the echoes of that first observed neutron-star collision reverberated through the halls of science, a profound realization settled in. We were witnessing the dawn of a new age of exploration, one where the universe would speak to us in vibrations as well as in rays of light. Gravitational wave signals may seem simple, a rising tone, a faint tremor in a detector, but they carry a wealth of information about the cosmos. Every nuance of a gravitational wave, from how its frequency changes to how long it lasts, tells a story about the cataclysm that generated it. From the neutron-star collision we observed, scientists could tell the masses of those stars and even glean hints about their size. The ripples in space-time functioned like a recording of the final dance. By playing back that recording with careful analysis, we learned how heavy each star was, how fast they spun around each other, and that together they likely collapsed into a black hole at the end. These signals confirmed many long-held theories, and also opened new questions. For instance, the gravitational wave from the neutron-star merger, combined with the flash of gamma rays, allowed scientists to verify that gravitational waves travel at the speed of light, just as Einstein's theory said. The fact that the gamma rays were detected just seconds after the gravitational waves, after both traveled over 100 million light-years, means they essentially raced neck and neck across the universe. Neither outran the other by more than a blink of an eye over that immense distance. Had gravity's waves traveled even slightly slower or faster than light, the gamma flash would have arrived much earlier or much later than the waves. Instead, they coincided almost perfectly, proving that space-time's ripples race along at light speed. This was a profound confirmation that space and time behave as expected, even in such extreme events. By studying the shape of the gravitational wave signal, researchers also probed the nature of neutron star matter. As the two stars spiraled in, they began to stretch and deform each other through tidal forces. These deformations left subtle imprints on the gravitational waves. From those imprints, scientists could infer how stiff or squishy neutron star material is. Essentially, how a neutron star's material responds to immense gravity. In practice, this means they could estimate the radius of a neutron star and how pressure builds inside it, narrowing down the possible models for what lies at a neutron star's core. This is something that cannot be fully tested in laboratories on Earth, because the densities inside a neutron star are beyond anything we can recreate. The gravitational waves provided a direct peek into the physics of ultra-dense matter, giving us clues about the state of matter at pressures millions of times higher than in an atomic nucleus. The combination of gravitational wave and electromagnetic observations also unlocked a treasure trove of insights about the broader universe. When astronomers identified the distant galaxy from which the neutron star collision's light came, they were able to measure its distance by traditional means. Meanwhile, the gravitational wave signal itself also carried information about how far it had traveled, based on its amplitude, much like a quiet sound suggests a faraway source. Comparing these two distance measures gave an independent check on the scale of the universe. In other words, we gained a new way to gauge how fast the universe is expanding. Each such collision can serve as a standard siren, a cosmic yardstick for measuring distance, and by extension, the expansion rate of space. It's akin to having a new kind of lighthouse across the cosmos, one that shines in gravity rather than light, helping us map the universe in a fresh way. As more of these cosmic beacons are observed, they will sharpen our understanding of the universe's expansion, complementing the insights gained from other measurement methods. Perhaps one of the most remarkable revelations was about the origin of some of the elements around us. The afterglow of the neutron star merger, observed in the days following the gravitational wave event, displayed signatures of newly forged heavy elements. For decades, scientists had suspected that when neutron stars collide, the debris flung out would create rare elements like gold, platinum, and uranium. The observations from the first detected merger confirmed this beyond doubt. In the spectra of the fading fireball, they found evidence of these heavy elements forming. This means that many of the atoms heavier than iron in the periodic table, atoms that make up parts of our planet and even our bodies, were likely created in neutron star collisions. Observations suggested that this single collision produced heavy elements equivalent to several times the mass of Earth in gold and platinum alone, finally solving a decades-long mystery of where about half of all elements heavier than iron are produced. The gold in a ring, or the iodine in our bodies, may have been forged in the fiery seconds following the merger of two neutron stars, billions of years ago and countless light years away. Those atoms were then scattered into space by the explosion, eventually becoming part of new stars, new planets, and perhaps even living beings. Gravitational waves have also revealed objects and phenomena that were invisible or hidden from traditional telescopes. Before these detections, we had never seen two black holes merge, because such an event emits no light. Yet the first gravitational wave detection was exactly that. Two black holes crashing together in darkness, unobservable by any telescope, but producing a clear signal in gravitational waves. This opened our eyes to a whole population of massive black holes and their violent unions that we previously only theorized about. It turned out that such mergers are relatively common in the universe. Gravitational wave observatories have since recorded many of them. These findings shed light on how black holes pair up and what masses they can have. Some of the black holes we have detected were more massive than scientists believed a single star could produce, a surprising revelation about the birth of these cosmic giants. The signals have consistently matched the predictions of general relativity, even in these extreme cosmic collisions. This is itself a powerful message. Einstein's century-old theory continues to hold true when two neutron stars collide, and when black holes merge, events far beyond the scale of any human experiment. Each new detection is not only an astronomical discovery, but also a test of fundamental physics. So far, the ripples in spacetime have shown no deviations from what our equations predict, giving us confidence that we understand these basic laws. at least for now. But scientists remain watchful. Each gravitational wave is scrutinized for any tiny anomaly, because even a subtle difference from predictions could herald new physics or reveal hidden features of the universe. If one day a signal arrives that doesn't fit our models, it could be the first whisper of phenomena beyond our current knowledge. For the moment, however, every observation has only reaffirmed the elegant accuracy of Einstein's vision. Beyond the specifics of each event, there is a broader revelation. The universe is filled with gravitational conversations that we were deaf to before. Every merger, every violent cosmic event sends out these ripples. Now that we can detect them, we are like listeners tuning into a once silent cosmos. We find that the cosmos has been alive with subtle symphonies, black holes merging, neutron stars colliding, including the collapse of stars in supernova explosions, each sending out its own faint contribution to the cosmic symphony. We have added a new dimension to our perception of the universe. What was once dark and silent can now be experienced in a new way. And with each signal we decode, we learn not only about distant stars and collisions, but also about the fundamental workings of reality on the grandest scales. In a way, gravitational waves have made the invisible visible, or rather, the inaudible audible. They confirm known truths, like where gold comes from and how fast the universe is expanding. They also uncover new mysteries, such as the unexpected abundance of massive black holes. Each ripple in spacetime is a messenger from events long past, traveling eons to reach us and enrich our understanding. By catching these messengers, we have begun to piece together a more complete story of the universe, one that includes not just the light of stars, but the vibrations of space itself as it responds to cosmic violence. This knowledge deepens our connection to the cosmos. We now know that when we look up at the night sky, the darkness between the stars is not empty silence. Instead, it is filled with a background chorus of hidden cosmic echoes, each one a story waiting to be heard. For the neutron stars themselves, everything we have discussed leads to one final act, the moment of collision. In their long journey, the last few seconds are by far the most intense. After millions of years of quiet orbiting, all the pent-up energy of the system is about to be released in an instant. As the two stars spiral inward, their orbit tightens and their speed skyrockets. Once leisurely circling in hours, they now complete multiple orbits in a single second. By this time, each star is hurtling around the other at a significant fraction of the speed of light. The immense gravity wells of each neutron star draw them together with unstoppable force, and nothing can prevent their impending union. With each millisecond, the distance between the stars shrinks. What was once a gap of thousands of kilometers narrows to a few hundred, then to virtually nothing. The stars begin to feel each other's presence in terrible detail. Tidal forces stretch and squeeze their crusts. The normally solid neutron star material strains under the gravity of its approaching twin. If one star is even slightly larger or less compact, it may start to deform or shed some mass, a thin stream of neutron-rich matter spiraling outward. The two dense spheres are now so close that if you could stand on one, an impossible feat, the other would loom huge in your sky, a rapidly enlarging orb racing around you in a blur. If you could stand on one of these neutron stars, an impossible feat of course, your view would defy imagination. The companion star would loom enormous and bright, whipping around the sky in a matter of hours. You would feel gravity millions of times stronger than Earth's, pinning you down with unbearable force, yet the other star's tug would try to lift you as it passed overhead. Time itself would run differently in such extreme gravity. This thought experiment shows just how alien and extreme a binary neutron star's environment truly is. The pitch of the gravitational song they produce rises to a crescendo. What started as a low-frequency hum has become a high-pitched whine, far above the range of human hearing, but unmistakable to detectors. These final orbits release a torrent of gravitational waves, carrying more energy away in a blink than the stars emitted in millions of years. Space itself shudders around the merging stars, rippling outward in waves that will travel across the universe. In these last instants, the gravitational waves are so strong that, could we perceive them directly, we might feel space quivering like the surface of a drum. To astrophysicists monitoring the detectors, this final crescendo is often described as a fleeting chirp, a swift rise in frequency and then sudden silence, the signature sound of two neutron stars finally becoming one. Time seems to compress as the end approaches. In the very last second before impact, the stars whirl around each other dozens of times. They are a blurred dance of unimaginable speed and power, two heavyweights on a collision course. By now, the neutron stars are almost touching. Their surfaces, composed of ultra-dense matter, begin to merge and distort under each other's gravity. A fraction of a second later, inevitability becomes reality. The two stars slam into one another. In that final moment, their cores collide with ferocious energy. The merger unleashes an explosion of phenomena. A massive shockwave rattles through the coalescing object, heating it to incredible temperatures. Any remaining crust of normal atoms is obliterated, and jets of high-energy radiation burst out from the polar regions. A flood of nearly invisible neutrinos, ghostly subatomic particles, also streams away from the hot, dense core. In the darkness of space, for a brief instant, a flash of gamma rays blazes out, announcing the birth of a new entity. The two neutron stars, which had danced as separate partners, have now become one. In that tiny fraction of a second, the power unleashed exceeds that of countless suns. An amount of energy rivaling a supernova's fury is released in an instant. What remains immediately after is likely a single, even more massive neutron star, or if the combined mass is great enough, it collapses further into a newborn black hole. Surrounding this merged core is a seething cloud of debris, a mix of neutron star material flung out by the violent collision. This debris is extremely hot and rich in neutrons, and it will soon shine with its own light as it expands outward. Inside the expanding debris cloud, atomic nuclei are smashed together and new heavy elements begin to form. In those first moments, the collision forges precious metals and other elements that will drift through space, eventually seeding future generations of stars and planets. But in the very first moments, before any light has had time to emerge, the gravitational waves and the gamma-ray flash have already carried the news of this cosmic catastrophe to the universe. The last few seconds of the inspiral are a scene of both violence and transformation. From orderly orbits and steady signals, the system erupts into chaos and brilliant energy. If one were somehow watching from a safe distance, one would see a sudden burst where there had been darkness, and space itself ringing and reverberating from the impact, as if a cosmic bell had been struck. In that blink of an eye, the binary neutron star system ceases to exist, replaced by an entirely new configuration of matter and energy. The event is over for the stars. They have met their fate. But for observers elsewhere in the cosmos, the story of this collision is just beginning to be told through the messengers it sends out. Those signals will carry the tale of the merger outward, to any who have the means to listen. The colossal merger of two neutron stars is an awe-inspiring event, but it is also exceedingly rare on human timescales. Still, astronomers do not have to simply wait in the dark for such accidents to happen. They can attempt to predict where and when these cosmic cataclysms might occur. By studying binary neutron star systems in our galaxy, Scientists have essentially foretold a few future collisions, albeit ones that will happen long after our civilization is gone. In 1974, two radio astronomers named Russell Hulse and Joseph Taylor discovered a strange pulsar that was periodically speeding up and slowing down in its pulses. It turned out this pulsar was in orbit around another neutron star, a binary system. By carefully tracking the pulse timings over years, they found the orbit was shrinking ever so slightly, exactly as Einstein's theory predicted. This binary pulsar allowed astronomers to calculate its fate with great precision. They found that the two neutron stars in that system are gradually spiraling inward and will merge in about 300 million years. Another double neutron star system discovered more recently is also doomed to merge on a shorter time frame. Calculations show it will collide in roughly 85 million years. These timescales are enormous, but they clearly indicate that the dance of doom does end, and that we can predict its finale if we are patient enough. To put it another way, we have identified ticking time bombs in the stellar remnants scattered through our galaxy. Each known neutron star pair comes with a sort of expiration date, an estimate of how long it will continue to orbit before the inevitable crash. None of the systems we currently know are due to collide anytime soon, at least not in the next few millennia. However, the fact that we can calculate their merger times at all is remarkable. The physics is so well understood that from the slight shortening of an orbital period, we can project the system's future millions of years ahead. We can essentially foretell the death of these binaries, even if we won't be there to witness it. It's a bit like predicting an eclipse, but on a vastly grander scale. Instead of the moon's shadow, we forecast the fiery collision of stars in galaxies millions of light years away. Each time one of these long-anticipated events is finally observed, it feels like a promise kept by the universe, a confirmation that our understanding was true. Beyond our Milky Way, prediction becomes more statistical in nature. We cannot pinpoint specific neutron star pairs in distant galaxies and mark our calendars for their collision. They are simply too far and too faint to observe in detail. But we can use what we know about stellar evolution and the population of stars to estimate how often such events should happen across the cosmos. Long before gravitational waves were first detected, astrophysicists ran calculations and simulations to guess the rate of neutron star mergers. They considered how many massive stars form binary systems, how often both would end up as neutron stars, and how long those pairs might take to merge. From these models, scientists predicted that in a galaxy like ours, a neutron star collision might occur only once in tens of thousands or even hundreds of thousands of years. That sounds extremely infrequent, and it is. But when you multiply that by the billions of galaxies in the universe, you realize that these spectacular collisions must be happening somewhere all the time. It was this realization that gave researchers confidence that instruments like LIGO could eventually catch the faint whispers of such mergers from distant galaxies. Indeed, even before we directly observed a neutron star merger, we had other hints that they were out there. Mysterious flashes of high-energy light, known as short gamma-ray bursts, had been detected by satellites for decades. They would appear without warning from random directions in space and fade quickly. The leading theory was that these bursts were caused by neutron star collisions in distant galaxies. Essentially, it was the universe's way of announcing that a collision had just taken place, even if we missed the gravitational wave signal. Astronomers predicted that if we could line up one of those gamma-ray bursts with a gravitational wave detection, we'd confirm the connection. That prediction came true spectacularly in 2017, when the gravitational waves from a neutron star merger were followed moments later by a gamma-ray burst. It was the fulfillment of a years-long expectation, turning a suspected cause into a confirmed reality. Now that we have operational gravitational wave observatories, there is a new form of prediction at play. When detectors catch the early signs of an inspiraling neutron star binary, even before the final collision, automated systems can alert astronomers around the world. Telescopes can then be trained on the region of sky where the signal is coming from, in the hope of witnessing the light show of the merger as it happens. In the 2017 event, for instance, within hours of the gravitational wave detection, astronomers had predicted a general location in the sky for the source and were already searching for a new glow in that region. They found one, confirming the collision's aftermath. In the future, as our detectors become more sensitive and our networks more global, we might even get a few seconds or minutes of advance notice before the final crash of distant neutron stars. One day, as our detectors become more sensitive and our networks more expansive, we might even receive a warning moments before the final crash of distant neutron stars. Such an alert could arrive seconds or minutes in advance of the actual merger. It would allow telescopes to be already watching, catching the very first flash of light from the explosion as it happens. For astronomers, this would be like witnessing a cosmic catastrophe unfold in real time, rather than only seeing its aftermath. As things stand, we can't forecast specific neutron star collisions in the near future with precision. The universe doesn't make appointments for us to put on our calendar. But we have become adept at reading the clues that hint at these events. We know which systems will merge in the far future, and we have a sense of how frequently collisions happen on a grand scale. We have models that predict how bright the explosions will be, what kinds of elements they will produce, and how the gravitational wave signal will appear. Every time a new collision is observed, it's like a prophecy fulfilled. One more confirmation that our understanding of these violent dances was correct. It's reminiscent of how ancient sky watchers must have felt when they first predicted an eclipse and then saw it happen. Our calculations give us confidence in our cosmic predictions, and when one of those anticipated events finally comes to pass, it feels like the universe nodding in agreement. Perhaps one of the most profound aspects of predicting such cataclysms is what it says about our place in the universe. We have gone from simply looking up at the stars in wonder to actually anticipating specific cosmic disasters eons before they occur. We can calculate the destiny of stars we will never see with our own eyes. It underscores that human curiosity and intellect can reach across both time and space. Once, we could scarcely predict the movements of our own sky. Now we chart the destinies of stars, light years away and epochs into the future. We, tiny inhabitants of a small planet, have attained the foresight to know the fate of distant suns long before they meet their end. And when those events finally happen, perhaps witnessed by other beings or future versions of ourselves, the predictions made today will stand as a testament to the power of scientific insight. There is also a legacy component to our predictions. One day, millions of years hence, some future observers may witness the very collisions we have calculated today. Perhaps a far future astronomer in a distant time will point their instruments at the remnants of a binary pulsar we identified in the 20th century, right on the schedule we predicted. In that moment, our present-day foresight would bridge across eons, connecting beings separated by unimaginable gulfs of time through the shared knowledge of a cosmic event. Such thoughts underscore how our science not only expands understanding now, but also reaches forward to distant generations, leaving a roadmap of the future sky. Even now, as our instruments listen and our telescopes watch, we know that somewhere in the universe, another pair of neutron stars is inching inexorably toward their fiery meeting. We might not know exactly where or when it will occur, but we know it will happen. For all we know, even at this very moment, A pair of neutron stars might be colliding in some far-flung galaxy, its waves and light already on their way toward us. We remain ever vigilant, knowing that at any time the heavens may unveil another one of these dramatic finales. It could be tomorrow, in a galaxy millions of light years away, or it could be 100 years from now, in a nearer corner of the cosmos. Whenever and wherever it does, we will be ready to catch its signals. The predictions have been made. The cosmos simply has to deliver on the inevitable. And when it does, the light and fury of that distant collision will become part of our story, a cosmic event we long knew would one day come to pass. In the stillness of space, two ancient neutron stars circle one another. These stellar remnants have been locked in a gravitational dance for eons, spiraling slowly closer with each passing epoch. What began as a leisurely waltz billions of years ago has become a dizzying whirl, the pair now whipping around each other dozens of times each second. Invisible ripples radiate outward as they spin, faint tremors in the very fabric of spacetime, carrying away energy and nudging the stars ever nearer to their fate. Each orbit they complete is slightly tighter than the last, an inescapable embrace drawing them closer to a final, fateful moment. There is no sound in the vacuum, no warning cry, only the silent curvature of space announcing their motion. Gravity has bound them in a fatal attraction, and now gravity will bring their long union to a dramatic end. Each of these small twirling stars is a marvel of density and gravity. A neutron star is only about 20 kilometers across, roughly the size of a city, yet it contains more mass than our Sun. These objects are the collapsed cores of once giant stars, crushed so tightly by past supernova explosions that atoms themselves have been obliterated, leaving behind immense spheres of neutrons. A single teaspoon of neutron star material would weigh billions of tons. The gravity on a neutron star is so immense that if an object were to fall from just 1 meter above its surface, it would hit the crust in a fraction of a millisecond, accelerated to incredible speed. Inside, the matter exists in an exotic state, a soup of subatomic particles with atoms smashed into a sea of neutrons, perhaps even stranger forms of matter at the core. This incredible density gives the stars a powerful gravitational pull, binding the binary pair in their tightening orbit. The two neutron stars, tiny yet unimaginably massive, continue their age-long dance, unaware that it is about to end. Now, at long last, the final moments arrive. The neutron stars have drawn so close that only a few hundred kilometers separate them, barely the breadth of a small moon's orbit, astonishingly near on a cosmic scale. They rush toward each other faster and faster, their orbital dance becoming a frantic blur of motion. In these last instants, each star hurtles through space at a sizable fraction of the speed of light. With each split-second whirl, space-time itself stretches and compresses under their weight, sending out ever stronger gravitational waves and building to a final crescendo. The stars begin to distort slightly, tidal forces warping their ultra-dense crusts as the inevitable collision looms. Every millisecond sees them drawing closer still, spiraling in with a desperate speed. In the final second, the pair might orbit each other dozens of times, a blur of incredible energy. Fractions of a second before merging, they whirl hundreds of times per second, the gap between them now just a few tens of kilometers. The inspiraling motion reaches a feverish pitch, far beyond anything we can directly perceive, yet still obedient to gravity's relentless pull. Inexorably, the gap closes to zero. The fatal moment is at hand. At last, the two neutron stars slam together as one. In that infinitesimal instant of impact, their cores physically merge, forming a single, ultra-dense mass. The combined mass is extraordinary, so heavy that even a neutron star's exotic matter can scarcely support it. For a brief moment, a supermassive neutron star might exist, wobbling and seething under its own tremendous gravity. But almost immediately, it collapses further, giving birth to a new black hole amid the chaos. The collision unleashes an unfathomable surge of energy, igniting a flash of gamma radiation brighter than 1 billion suns. Space itself rings like a struck bell, sending gravitational tremors racing outward at light speed. Eons of orbiting and slow decay have led to this instant, a final cosmic crescendo that is over in the blink of an eye. A moment ago, this doomed binary was nearly invisible in the darkness of space. Neutron stars emit little visible light, so their final approach unfolded without any spectacular glow. But with the collision, that changes in an instant. What was once a dark, silent dance now becomes a cosmic fireworks display of the highest order. The previously unseen pair announce their grand finale with a sudden blaze of energy, a beacon visible across unimaginable distances, though not to human eyes in the usual sense. Instead of sound, their announcement comes in the form of intense light and the rippling of spacetime, proclaiming a dramatic conclusion to their story. Yet even in this immense violence, the spectacle remains eerily silent. In the vacuum of space there is no air to carry sound. No boom or crash accompanies the smash of the stars. The neutron stars merge in ghostly silence, with only light and invisible gravitational waves to herald the event. It is a paradox of the cosmos, an unimaginable explosion unfolding in perfect quiet, its fury witnessed only by the signals it sends out. In the immediate aftermath, chaos reigns at the collision site. Fragments of neutron star matter are flung outward, and a swirling disk of superheated debris surrounds the newborn black hole. The merged object, likely a nascent black hole cloaked in a halo of plasma, now begins to mold the carnage around it. Amid the turmoil, 2 focused beams of energy punch through the debris. From the north and south poles of the merged mass, powerful jets erupt, shooting outward at nearly the speed of light. Intense magnetic fields, twisted by the fury of the merger, help channel these beams into tight, blazing columns that blast away from the collision. These jets carry an intense burst of high-energy radiation, largely gamma rays. This flood of light serves as a cosmic beacon, announcing the violent event to the universe. Though the crash itself is shrouded inside swirling wreckage, the piercing signal of the jets cuts through the darkness of space, racing outward to spread the news of what has occurred. Far away from the collision site, the first signal to reach distant observers is a storm of gamma radiation. This torrent of high-energy light erupts from the newborn black hole's jets and rushes through space at the ultimate speed limit, the speed of light. In mere seconds, it has travelled millions of kilometres, racing outward across the cosmos like an expanding flashbulb. This is a gamma-ray burst, a sudden and intense flash of the universe's most energetic light, unleashed by the neutron star's violent merger. For a brief moment, it outshines almost everything else in the entire sky, releasing more energy in a blink than millions of stars do in years. And then, as quickly as it came, the brilliant flash fades, gone in a matter of seconds, leaving the cosmos dark once more. For an event of such incredible power, it is astonishing how fleeting it is. One moment the gamma blaze is there, the next moment it's gone, and the sky returns to quiet darkness. If you had blinked at the wrong time, you would have missed it entirely. Only our ever-watchful instruments, recording the sky in gamma rays, caught its full fury and its rapid fade-out. Such brevity in the face of such energy is part of what makes gamma-ray bursts so mysterious and captivating. They are like cosmic flashbulbs or firecrackers, explosive bursts of light that are here and then gone in the blink of an eye, leaving us to wonder what mighty event produced them. Gamma rays are the highest energy form of light, far beyond ultraviolet light or even X-rays. They are invisible to human eyes and incredibly penetrating, arising only from the most extreme events in the universe. During the neutron star collision, subatomic particles in the jets were accelerated to nearly light speed, generating this searing gamma flash. For those few seconds, the burst's luminosity was almost inconceivable, by some measures, as luminous as 1,000,000 trillion suns. Such power is difficult to imagine, yet it was released and spent in the blink of an eye, like a cosmic camera flash illuminating the darkness for a mere heartbeat. The sheer intensity and suddenness of this light make gamma-ray bursts one of the most awe-inspiring phenomena known, a literal flash of fury in the depths of space. Gamma-ray bursts, or GRBS, have long been one of astronomy's great enigmas. Back in the late 1960s, at the height of the Cold War, satellites designed to monitor nuclear bomb tests unexpectedly detected intense flashes of gamma rays coming from space rather than Earth. These mysterious signals, clearly not of human origin, were the first hints of GRBS. For years afterward, such bursts of gamma light appeared without warning and vanished almost instantly, leaving scientists puzzled and debates raging. It became clear through observation that gamma-ray bursts were exceedingly powerful and came from far beyond our solar system, likely from distant galaxies. But what could produce such an intense blink of gamma radiation remained a mystery for decades, sparking theories that ranged from colliding stars to massive supernova explosions to the collapse of exotic objects like hypothetical hypernovae or even evaporating black holes. GRBs were cosmic whodunits, their origins hidden behind the briefness of their appearance. Over time, astronomers learned that there are different types of GRBS. Some last for long durations, tens of seconds or even minutes, and were eventually linked to the explosive deaths of massive stars, Titanic, supernovae, or hypernovae, collapsing into black holes. But the short bursts, those lasting only a couple of seconds or less, were suspected to come from a different phenomenon altogether, perhaps the catastrophic mergers of compact objects like neutron stars. For decades, neutron star collisions were a top contender in scientific theories as the source of short GRBs. Now, with this cosmic collision, that hypothesis has been dramatically confirmed. The merger of two neutron stars can indeed launch a short gamma-ray burst. The fleeting 2-second flash from these colliding stars served as a cosmic announcement that a new black hole had been born and that the long-standing mystery of short GRB origins was solved. It is only by fortune of alignment that we on Earth witnessed this gamma outburst at all. The jets of gamma rays are like narrow searchlight beams sweeping through the cosmos. If our planet lies outside those beams, the burst would pass unseen, its energy focused in another direction entirely. In this case, one of the jets happened to be aimed close enough to Earth's line of sight that space-based detectors recorded the flash. Energies this high do not penetrate Earth's atmosphere, so only instruments in space could sense it. Even so, the burst wasn't blindingly bright by gamma-ray standards, implying that we observed it slightly off-center, not directly in the beam's path. Had we been looking straight down the barrel of the jet, the flash would have been far more intense and energetic. This orientation factor helps explain why only some neutron star mergers produce observable GRBs. Many others shine their fury in a direction that never intersects Earth, remaining unseen to us. It also underscores how lucky and significant this detection was. By catching even a glancing blow of the gamma jet, we were able to witness an event that would otherwise have been hidden. Yet this burst of gamma rays is only one chapter of the story. The neutron-star collision did not merely create light. It also sent out other kinds of cosmic messengers that we could detect. While the flash of high-energy light fades, the universe still trembles from the merger in other ways, and new signals begin to trickle in. In the moments and hours following the collision, a symphony of different messages fans out across space. Not just light, but gravitational waves and perhaps elusive particles, each carrying a piece of the story of this stellar cataclysm. The true power of this event comes into focus only when we combine all these messages, a task perfectly suited to the new era of multi-messenger astronomy. The neutron star's final performance is not a solo, but a symphony of cosmic signals. In one momentous instant, the universe broadcasts on multiple channels at once: electromagnetic light, gravitational waves, and even whisper-quiet particles, each a different instrument playing in unison. This is the essence of multi-messenger astronomy, observing celestial events through every available cosmic messenger. Just as a full orchestra delivers a richer experience than a single violin, the combination of these cosmic messengers provides a far deeper understanding of the event than any one signal alone could offer. The collision of two neutron stars produced not just a flash of light, but a chorus of distinct signals, all traveling across space together, each one contributing its own notes to the cosmic melody. First among these cosmic musicians are the gravitational waves, literal ripples in space-time itself, set off by the inspiraling stars. As the neutron stars orbited and merged, they continuously sent out waves that stretched and squeezed the fabric of the universe around them. Those waves raced away at light speed, carrying with them a detailed record of the collision's choreography. By the time they reached Earth, the distortions they caused in space were incredibly small, on the order of a fraction of an atom's nucleus, yet our exquisitely sensitive detectors felt them. In observatories equipped with giant laser interferometers, scientists heard the gentle chirp of these waves, a rising tone that corresponded to the final spirals and ultimate merger of the neutron stars. It was the unmistakable vibration of two stars crashing together, arriving at our planet after traveling 130 million years through silent space. To put that in perspective, those waves set out when dinosaurs still roamed the Earth, and only now have they reached our detectors. Remarkably, in this event, the gravitational waves were detected just moments before the burst of gamma rays arrived. About 1.7 seconds after the ripples in space-time passed Earth, our space telescopes caught the gamma flash from the very same source. This tiny difference in arrival time confirmed that gravitational waves travel at essentially the same speed as light, a key prediction of Einstein's general relativity. It also revealed a physical truth about the merger. The gamma rays were emitted almost immediately after the stars coalesced, likely once the newly formed black hole's jets punched through the ejected debris. For astronomers, seeing these two signals in concert was like witnessing thunder and lightning from a cosmic storm, the flash of light and the space-time tremor arriving nearly together, proving they came from one tremendous event. It was an unprecedented achievement, the first time an astronomical event had been observed in both gravitational waves and electromagnetic light, heralding a new era of truly multi-messenger exploration of the universe. And the symphony did not stop with gamma rays. Within hours of the merger, dozens of telescopes around the world swiveled to the patch of sky pinpointed by the gravitational wave and gamma ray signals. At optical and infrared wavelengths, observers discovered a brand new pinpoint of light in a distant galaxy, the glow of the collision's aftermath, known as a kilonova. This kilonova, essentially a transient astronomical event caused by the radioactive decay of newly formed elements, first shone in a brilliant bluish hue. The visible and infrared light coming from the expanding debris carried unmistakable fingerprints of heavy elements that had been forged in the explosion. In the days and weeks following the event, X-ray and radio telescopes also picked up faint afterglows emanating from the merger site, generated as the ejected material and the jets interacted with the surrounding interstellar medium. Each part of the electromagnetic spectrum, from high-energy gamma rays and X-rays down through visible light and to long-wavelength radio waves, contributed another piece of the puzzle, revealing different facets of the cosmic collision's aftermath. By combining them, scientists could build a comprehensive picture of what transpired. Beyond light and gravitational waves, scientists also listened for other, even more ghostly messengers. Neutrinos, nearly massless subatomic particles, are often produced in tremendous numbers by cataclysmic events like supernovae, and possibly by neutron star mergers as well. These elusive particles stream through matter almost unimpeded, carrying information from deep within the heart of the explosion. For this neutron star merger, no neutrinos were definitively detected. Not surprising, given the distance and that a merger might produce fewer neutrinos than a supernova. Nonetheless, the very act of checking for neutrinos was important. It demonstrated how thoroughly astronomers now examine cosmic events, attempting to catch every possible signal the universe offers. In the future, should a neutron star collision occur closer to us, a flood of neutrinos might be captured by detectors on Earth, adding yet another voice to the cosmic chorus and allowing us to peer directly into the nuclear forge at the moment of element creation. Bringing together all these messengers, light, gravitational waves, and particles, has painted an extraordinarily rich picture of this neutron star collision. The gravitational wave sound told us about the masses of the stars and the precise timing of their merger. The gamma rays signaled the birth of the black hole and the fierce formation of jets. The optical and infrared light unveiled the creation of heavy elements in the ejected debris. The X-ray and radio afterglows confirmed the presence and structure of the energetic jets as they ploughed into their environment. Each type of observation reinforced and complemented the others, confirming theories on one hand, while revealing new surprises on the other. It's as if nature allowed us to both hear and see a cosmic event simultaneously, a multisensory experience on a galactic scale, rich with information. Perhaps the most profound revelation from this multi-messenger campaign was proof of a kind of cosmic alchemy at work. The optical spectrum of the kilonova's fading glow showed distinctive fingerprints of newly created elements, confirming that this collision forged heavy atoms, including gold and platinum, in tremendous quantities. This discovery answered a long-standing question in astrophysics. Where are the universe's heaviest elements made? The observations provided direct evidence that neutron star mergers are one of the foundries. By combining what we heard in gravitational waves with what we saw in light, scientists were effectively watching elements being born in real-time time, deep in the merger's debris cloud. With the evidence gleaned from this single event, we now turn to examine that process itself, the cosmic crucible by which such collisions create the gold, platinum, and other heavy elements that we value so deeply. For centuries, alchemists on Earth sought in vain to transmute lead into gold. Little did they know, the universe was already performing such alchemy on an unfathomable scale, not in earthly laboratories, but in the hearts of exploding stars and colliding stellar remnants. Within the debris of this stellar collision, nature performs a true alchemical feat. In the split seconds after the neutron stars merge, an immense crucible of nuclear reactions ignites. Neutron-rich material, ripped from the stars, and now superheated to billions of degrees, becomes the seedbed for forging new atomic nuclei. Scientists had long wondered where the cosmos manufactures its gold, platinum, uranium, and other heavy elements. Here, in the heart of a neutron-star merger, lies the answer. These cosmic forges create the precious metals and rare elements, transmuting the raw fury of the collision into the fundamental ingredients of planets, minerals, and even living beings. Out of destruction comes creation. The violent merger turns mere neutrons and lighter nuclei into some of the heaviest atoms in existence. In a single flash, nature accomplishes what human alchemists could only dream of, turning matter into gold and much more on a colossal scale. Normal stars, in their hot cores, confuse lighter elements into heavier ones up to iron. But creating elements heavier than iron, such as gold, lead, or uranium, requires a wholly different process and far more extreme conditions. It demands an environment flooded with free neutrons and titanic bursts of energy, conditions not found in the hearts of ordinary stars. For decades, astronomers suspected that supernova explosions, the deaths of massive stars, might provide those conditions, and indeed supernovae do forge some heavy elements. Yet calculations showed that even the most powerful supernovae could not account for the full abundance of the heaviest elements: gold, platinum, rare earth elements, uranium, observed in the universe. There seemed to be a gap. An additional source was needed to fill the periodic table's upper range. Merging neutron stars, with their neutron-saturated matter and explosive energy, emerged as a prime suspect. Now, the observations of this event have decisively validated that idea. We finally see that neutron-star collisions are a major, if not dominant, source of the universe's heaviest chemical elements. Inside the expanding debris cloud of the merger, atomic nuclei are bombarded by an onrush of free neutrons. In mere seconds, nuclei of lighter elements, like iron, rapidly capture neutron after neutron, a process aptly named rapid neutron capture, or the R process. This furious barrage overwhelms the nuclei, pushing them to balloon into extremely heavy, unstable isotopes. When the neutron storm subsides, these oversized nuclei begin to decay into more stable forms, transforming themselves into new, heavier elements in the process. In this way, elements much heavier than iron, from silver and iodine to gold and platinum, even up to uranium, are synthesized in the blink of an eye. All of this happens in the seething debris cloud as it races outward. The collision provides both the raw material, countless free neutrons, and the intense energy needed to build and mold these heavy nuclei. It is like a cosmic blacksmith's forge operating at incredible speed, hammering atomic particles together to create the universe's heaviest treasures. Amazingly, astronomers actually witnessed direct evidence of this element forging process by dissecting the light of the kilonova. The glow from the debris carried telltale spectral lines, specific colors of light that serve as fingerprints for certain elements. In the case of this merger, the distinct signature of the element strontium was identified in the optical spectrum of the aftermath. This marked the first time we've seen clear proof of a freshly minted heavy element, strontium, born out of a neutron star collision. That detection was a triumphant moment in science, showing that neutron stars aren't just made of neutrons. When they collide, they scatter those neutrons in a form that builds new elements. It confirmed that what theory had long predicted was really happening. The merger's debris cloud was transmuting into a treasure trove of new atoms. The periodic table was being written in real time by the fire of the collision, and we were lucky enough to read a few lines of it via our telescopes. The sheer quantity of heavy elements synthesized in one such event is staggering. Scientists estimate that this single collision created heavy elements with a total mass several times that of Earth. Incredibly, a significant portion of that yield may have been gold and platinum, possibly on the order of a few Earth masses worth of just these two precious metals. Imagining so much gold forming almost instantaneously challenges the imagination. It is as though countless planet-sized vaults of treasure were forged in an instant and scattered into space. Of course, these metals were not produced as solid bars or ingots, but as microscopic atoms and fine particles dispersed in a radioactive vapor. Still, the comparison highlights the almost unfathomable creative power of a neutron star merger. In a matter of seconds, more gold and platinum can be made than what resides in entire star systems. It's a cosmic mint, coining precious metal on a monumental scale, then flinging it out into the galaxy. This discovery has fundamentally changed our understanding of cosmic chemistry. It appears that a large fraction of the universe's supply of elements heavier than iron, including many that are essential for life and human civilization, originates from cataclysms like neutron star mergers. Every gold ring on a finger, every bit of platinum in a computer or jewelry box, likely owes its existence to one of these catastrophic mergers that occurred billions of years ago. These events are rare on human timescales, but over the life of a galaxy, they happen often enough to steadily enrich the galactic environment with heavy elements. In a very real sense, neutron star collisions have seeded the cosmos with ingredients that later form planets and even play roles in biology and geology. For example, elements like iodine are crucial for life, and uranium helps warm planetary cores. We on Earth are literally wearing and handling the remnants of ancient cosmic explosions. Once created, these heavy elements do not stay confined to the merger site. The tremendous blast expels them far out into surrounding space, mixing them with the interstellar gas and dust of the galaxy. The newly forged atoms are cast outward at enormous speeds, forming an expanding cloud of radioactive debris racing away from the collision. As this cloud spreads and cools over years and centuries, its contents, gold, platinum, neodymium, uranium, and many more, begin to blend into the interstellar medium, the diffuse gas between the stars. What was once concentrated in a tiny binary system is now on its way to becoming part of the wider galaxy, carried by the blast's momentum far from the scene of the merger. Over time, the distinct signature of this particular event will fade as its material dilutes and becomes just another part of the galaxy's makeup. But those atoms will not disappear. They will simply become part of something new. In the following millennia, the ejecta from the collision continues to drift and diffuse through space. The precious atoms, gold, platinum, iodine, uranium, and all the rest, ride the shockwave fronts outward, dispersing into ever more tenuous concentrations. Eventually, they may merge into nearby nebulas, enriching vast clouds of gas and dust that span light years. Within those giant molecular clouds, these heavy elements mix with primordial hydrogen and helium, becoming part of the raw material for future generations of stars. When gravity causes one of these enriched clouds to collapse and form new stars and planets, the heavy elements from that long-ago neutron star collision are incorporated into those new worlds. In this way, the products of a single cataclysmic event end up spread across many star systems over time, seeding far-off environments with elements that originated in a single explosive moment. Imagine, for instance, a single atom of gold forged in the collision. In the aftermath, it hurtles outward, embedded in the expanding debris cloud. For millions of years, it may drift through the galaxy, perhaps wandering through tenuous nebula, or simply floating in the space between stars. Eventually, it could find itself drawn into a collapsing cloud that is forming a new solar system. That lone gold atom might become part of a young planet, perhaps locked in a vein of ore in the planet's crust, or dissolved in its molten core, or it might even circulate in the waters of an ocean if that planet develops life-sustaining seas. In that manner, a direct piece of the neutron star's final death dance can end up quietly embedded in a world far removed from the original collision. A single atom's journey from a cosmic explosion to possibly glimmering in a rock on a distant planet is a dramatic illustration of how intimately connected the universe is. Our own solar system likely benefited from this cosmic recycling. Long before the Sun and Earth formed, the gas and dust that would eventually coalesce into our solar system was seeded by earlier generations of stars, and at least one neutron star merger as well. Embedded in that primordial cloud were traces of heavy elements from ancient stellar collisions. When our Sun ignited and the planets formed around it, those heavy elements became part of Earth's rocks, our oceans, and even our bodies. This means a distant neutron star collision, perhaps billions of years ago in the Milky Way, contributed atoms to our planet. The gold in a wedding ring, the platinum in an electronic circuit, even the iodine in the human thyroid. These can be thought of as messages from long-forgotten cosmic explosions, delivered across time and space to become part of us. We are, quite literally, wearing the remnants of neutron star collisions that predate human civilization. The rarity of these elements on Earth reflects the rarity of their cosmic origin. Neutron star collisions are infrequent. In a galaxy like the Milky Way, such an event might occur only once in tens of thousands of years. Yet, over billions of years, even these sparse occurrences have filled our galaxy with small but significant enrichments of heavy elements. That scarcity is precisely why metals like gold and platinum are so precious. They were forged in extraordinary celestial events and are not easily made or replaced. When we hold a piece of gold, we are holding the outcome of an immensely rare astrophysical calamity, a fragment of neutron stars' death throes that travelled across the galaxy and became part of our world. Understanding that origin lends these metals an almost sacred quality. They are artifacts of cosmic violence, tamed and brought into our daily lives as symbols of beauty and value. In this grand cosmic cycle, the violent death throes of stars ultimately contribute to the birth of new stars and planets enriched with heavy elements. Each neutron star collision is both an ending and a beginning, the end of two stellar remnants as separate objects, and the beginning of countless new possibilities for the matter they spewed forth. The galaxy slowly stirs these ingredients together, ensuring that even the most catastrophic events feed into the creation of future worlds. It's a profound truth of the universe. Destruction and creation are intertwined. The gold we cherish, the elements our technologies and bodies rely on, were forged in stellar fire and carried across the cosmos to become part of us. The journey of those atoms, from the heart of a neutron star merger to the soil of Earth, is a story of cosmic connectivity spanning time and space. It's often said that we are made of stardust, and in the case of these heavy elements, it's wonderfully true. We are children of cosmic fire and cosmic collisions. Once the neutron star collision has run its course, an extraordinary light fades and darkness returns. But even after the spectacular explosions and element forging, the event leaves behind echoes of fire that slowly diminish. Long after the initial flash has subsided, the aftermath of the collision continues to glow faintly. These are the fading embers of the cosmic fire, afterglows that shine across multiple wavelengths as the energy of the event is gradually released into space. In the hours and days following the merger, the kilonova's visible light burns at its brightest. Initially, that light is a hot, blue-white glow, fueled by the most extreme, fast-moving debris rich in lighter, heavy elements. But as the days turn to weeks and the debris cloud expands and cools, the light shifts to a softer red hue. This change of color, from blue to red, is itself a story. It reflects how the ejected material is evolving, with heavier, opaque elements, like lanthanides, dominating the opacity and cooling the glow into the red part of the spectrum. The shifting palette of the kilonova, from brilliant blue to somber red, told astronomers that the fireball was cooling and that different elements were revealing themselves over time. Watching this is like watching the embers of a fire change color as they cool, a visual narrative of the physics taking place in the aftermath. Meanwhile, other echoes of the explosion emerged on different timescales and at different energies. A few days after the merger, space observatories detected a faint X-ray glow emanating from the collision's location. About 2 weeks after the event, giant radio telescopes on Earth began to pick up radio waves from the same spot. These delayed signals were produced as the high-speed jets and debris from the merger ploughed into the surrounding interstellar medium, generating shock waves that heated particles and made them radiate. At first, these afterglows were very weak, almost imperceptible, but in the weeks following the merger, the X-ray and radio emissions slowly grew stronger. The outflowing jet, having expanded and slowed somewhat, was transferring energy to the gas around it, and that interaction glowed in X-ray and radio frequencies. Bit by bit, the afterglow brightened, reached a peak, and then eventually began to wane as the blast's energy dispersed into space. For months, astronomers kept their instruments trained on the merger site, tracking the fading X-ray and radio signals. Through these observations, they essentially watched the expanding blast wave and gleaned information about the structure of the jets. The data showed that material was indeed moving at relativistic speeds, a significant fraction of light speed, confirming that a narrow, powerful jet had been launched during the merger and was now slowing down and spreading out. Each fading signal carried new pieces of the story. By analyzing how the afterglow brightened and dimmed over time, scientists were able to infer the geometry of the jets and our viewing angle. The fact that the radio afterglow took many weeks to reach its peak brightness, for example, revealed that we were not looking straight down the jet, but rather viewing it from the side. If Earth had been directly in the jet's line of fire, the early emission, especially the gamma-ray burst, would have been far more intense, and the afterglow would have peaked sooner. Instead, the slower rise and fall of the afterglow told researchers that the jets were initially narrow and that we were off-axis, catching only the fringes of the beam. From these afterglow measurements, they could reconstruct a three-dimensional picture of how the explosion's blast propagated. It's a bit like hearing an echo in a canyon. By studying the echo's delay and strength, you can deduce the shape of the canyon walls. Here, by studying the afterglow's evolution, scientists deduced the shape and opening angle of the merger's jets, as well as how much energy they carried and how the energy was distributed. Even in its twilight, the event continued to teach us, each observation adding nuance to the tale of the collision. As months turned into years, the afterglow steadily weakened. Eventually, it slipped below the threshold of detectability. The fires of the neutron star collision had finally died down to darkness. The once brilliant beacon in that distant galaxy faded back into the quiet background of space. In the galaxy where this happened, a galaxy called NGC 4993 in the constellation Hydra, as we later learned, nothing visibly obvious remains to mark the site of the Great Merger. To an ordinary telescope now, it looks just like any other point in the sky. Yet the legacy of that moment endures in multiple forms. in the enriched matter now drifting through that galaxy, in the vast troves of data recorded by our observatories, and in the profound lessons we've learned about physics, astrophysics, and the origins of the elements. Astronomers will be analysing the measurements from this event for years, if not decades, to come, squeezing out every bit of knowledge about gravity, dense matter, and light. The collision may have faded from view, but it lives on in our understanding and has opened a new chapter of discovery. The story of this neutron-star collision, from the slow spiral to the final crash, and through the fading afterglow, illustrates how transient yet illuminating such cosmic events are. One brief moment of cosmic violence has given us insights that will enrich science for a generation. And there will be more. With advanced gravitational wave detectors and ever-alert telescopes, astronomers expect to capture many more neutron-star mergers in the coming years. Each new event will be another opportunity to listen to the cosmos and watch as new light and elements are born. For now, the echoes of this particular collision have faded into silence and darkness, but its light and fury live on in the knowledge we gained. The cosmic stage is set for the next act. Somewhere, in some far corner of the universe, another pair of neutron stars are spiraling together, and another celestial performance awaits. We, on our tiny planet, wait for the next whisper or shout from the universe to continue the tale, eager to learn what new wonders the cosmos will reveal next. For a breathless moment after the catastrophic collision of two neutron stars, it is as if the cosmos itself holds its silence. The furious light of the explosion has begun to fade, and the space-time ripples of the merger rush outward into the vastness. At the epicenter of this cosmic upheaval, something new and profound is taking shape in the quiet aftermath. Where once two ultra-dense stars tore each other apart in a final embrace, now their fused core is collapsing inward, giving birth to one of the most mysterious entities in the universe. In these first instants, all the energy and mass crushed into the merged core overwhelm even the mightiest forces of matter. The combined remnant has no stable form left to cling to. Gravity is winning an inexorable victory. In an implosion of almost unimaginable speed and force, the core caves in on itself. What emerges from this collapse is no ordinary object at all, but a region of pure gravity, a newborn black hole. It forms, suddenly, an invisible sphere delineated only by an event horizon, the boundary beyond which nothing can return. In the blink of an eye, the last remnants of the neutron stars vanish behind a veil of darkness that not even light can penetrate. The birth of this black hole is a transformation, both violent and eerily silent. No solid surface marks its presence now, only a shadow in space-time, a gravitational trap from which escape is impossible. All the mass of the two neutron stars is concentrated in an essentially bottomless pit of gravity. If we could hover nearby, safely distant, of course, we would see space itself bending steeply into a dark center. If there were stars aligned behind this darkness, their light would warp around the invisible object, forming a ring of brightness that outlines the void. This subtle halo would be one of the few visual hints that a black hole is there at all. The new black hole itself may be only a few tens of kilometers across, unimaginably small on cosmic scales, yet it contains more mass than our Sun. That mass is swallowed into a volume so tiny that the mind struggles to comprehend it. For a brief time, the newborn black hole rings like a struck bell. The fabric of space-time vibrates with the final echoes of the collapse, gravitational waves emitted as the hole settles into its new form. These gravitational ring-down signals are the dying tones of the merger, a fading whisper in the dark that observatories far away might just catch. The black hole itself, however, emits no light. It's a one-way door. Matter and light can fall in, but none can ever emerge to tell what they found on the other side. The violent birth we witnessed now gives way to an immense hush, as if the universe has sealed away the chaos inside this dark new entity. Yet around that silence, chaos still lingers in the outside world. Not all the matter was consumed by the black hole's formation. A halo of superheated debris surrounds the newborn void, swirling in orbit instead of falling in. This leftover material forms a frantic accretion disk, racing around the black hole at nearly the speed of light. It glows fiercely with high-energy radiation as particles collide and heat up in their desperate spiral. Magnetic fields tangle and crackle throughout the disk's swirling maelstrom. In the shadows of the nascent black hole, this disk of matter becomes a last beacon, a final signpost of the cataclysm that created the black hole, shining even as the core itself has gone dark. In cosmic terms, the entire birth of a black hole from two merging neutron stars happens in an instant. One moment, there are two distinct stars. The next, an enveloping darkness has taken their place. This outcome is the ultimate end state for such a merger when conditions are extreme enough, when the combined mass pushes beyond any conceivable threshold of stability. Gravity knows no mercy. If the unified star is too heavy, no force in nature can keep it from collapsing. And so, often, a black hole is the final result, marking the collision's aftermath with a gravitational well so deep that even light is captive to it. Where once there were neutron stars, solid, tangible, if extraordinary, objects, there is now a region of spacetime where the very concept of a surface or material has ceased to exist. This newborn black hole is a paradox of creation through destruction. It is a child of violence, born from the ruin of two stars. Yet in its birth, it has erased nearly all evidence of what came before. Inside its horizon might lie the crushed memory of those stars, their mass, their gravity, but nothing of their light or structure. To an outside observer, the black hole is simply an absence, a gravitational shadow. And as the debris settles and the fierce glow of the accretion disk begins to subside, even that shadow becomes calm. In the emptiness that follows, we are left to contemplate what has just occurred. The genesis of an object so extreme that it challenges our understanding of physics and reality. Yet cosmic fate can sometimes pause at the brink of collapse. Not every neutron-star collision is immediately claimed by darkness. Under certain conditions, the merged core can cling to existence a little longer, defying gravity for a fleeting moment. Before the darkness fully settles, there can be this momentary reprieve, the brief life of a hypermassive neutron star, a final stand against gravity's pull. For a brief span, the merged neutron star defies the fate of immediate collapse. In those special cases where conditions align just right, the two neutron stars combine into one colossal, overstuffed neutron star instead of a black hole, at least for a little while. This newborn titan is a hypermassive neutron star, an object heavier than any stable star could normally be. It is a cosmic anomaly, teetering on the very edge of existence, held up by the sheer fury of its own motion and internal pressure. This hypermassive survivor is a frantic, whirling dervish of a star. It spins at an incredible rate, wound up by the orbital dance of the two original stars now merged into one. Centrifugal force from this rapid rotation provides a temporary counterbalance to gravity's pull. For a moment, it is as if the star refuses to yield. It uses its spin like a ballerina twirling desperately to stay upright. The merged core is blazing hot as well. The collision has heated it to temperatures far beyond those in a normal neutron star. Its interior seethes with exotic particles, and maybe even phases of matter we have never seen, as the extreme density and heat push physics to its limits. Such a star can only exist on borrowed time. Every millisecond that passes sees it losing energy and angular momentum. It might fling waves of gravitational energy into space as it oscillates and quakes under the stress. It likely emits torrents of neutrinos, ghostly, nearly undetectable particles, as it tries to cool and shed some of the immense heat. Bit by bit, these processes sap the hypermassive neutron star of the forces propping it up. The rotation slows, or the thermal pressure eases just enough, and gravity tightens its grip. The equilibrium was always precarious. Now it begins to unravel. To an outside observer, this ephemeral star's life would be over almost as soon as it began. In many simulations and theories, a hypermassive neutron star born from a merger might survive only a few tens of milliseconds before collapsing. In some cases, if the mass is just barely above the collapse threshold, it might hold together for a second or two. A single precious heartbeat of time on cosmic scales. Indeed, astronomers believe they saw evidence of one such brief reprieve in an event observed from Earth not long ago. The aftermath of that neutron star collision suggested that the merged object stuck around for perhaps 1 second before it, too, crumbled into a black hole. 1 second of fragile existence. Then the darkness took over. As the inevitable collapse approaches, the hypermassive neutron star grows ever more unstable. It's like a spinning top that begins to wobble when it slows down. Once perfectly balanced, now lurching. The star's shape might distort. It could bulge at the equator from its mad rotation and then start to sag as gravity wins out. Cracks and fissures in its structure, not literal cracks in a solid surface, since a neutron star is more fluid than solid, but cracks in the stability of its configuration begins to appear. Finally, the moment comes when no force can hold it up any longer. In a final catastrophic instant, the core collapses inward. The massive neutron star, which briefly shone as one of the densest objects in the universe to still possess a surface, vanishes behind a newborn event horizon. The hypermassive neutron star's rebellion against gravity ends, and a black hole now firmly occupies its place. This final collapse is not a quiet surrender. When the hypermassive neutron star gives in, it does so dramatically. The sudden formation of a black hole at its center releases a deluge of energy into the surrounding debris. The collapse may generate a powerful shockwave, a last outward gasp that slams into the material around it. Any remaining fragments of the star's outer layers are cast off like a shed cloak as the core disappears. This violent end momentarily reinvigorates the wreckage of the collision around the black hole. It's as though the neutron star's final act is to kick outward, sending one more jolt through the matter that was once part of it. With that collapse, the stage is set anew. Now there is a black hole encircled by swirling debris, a scene not unlike what we encountered earlier, but reached by a delayed route. And that black hole, with its fiercely spinning disk of material, is ready to power one of the most spectacular phenomena of the merger. In the instant after the hypermassive star's fall, twin jets of astonishing power can erupt from the poles of the spinning black hole and disk system. Like cosmic searchlights, they pierce through the debris and darkness, announcing the event to the far reaches of the universe. The brief life of the hypermassive neutron star has ended, but in its dying moment, it hands the torch to these brilliant jets, which now carry the story of the collision outward into space. From the swirling chaos around the newborn black hole, something spectacular now takes shape. Intense magnetic fields threading through the hot accretion disk twist and tighten like coiled springs. In a sudden release, they channel some of the infalling matter and energy into two narrow funnels, one shooting out above the black hole's north pole, the other below its south pole. Thus are born the twin jets, focused streams of plasma and radiation that blast away from the merger site at nearly the speed of light. Each jet is an extremely collimated beam, a spear of energy piercing the surrounding space. Particles within them are accelerated to almost light speed, riding along those tightly wound magnetic fields as if on rails. Shock waves within the jets heat the material to incandescent temperatures, causing it to radiate furiously in high-energy light. In those first moments, as the jets punch through the debris cloud thrown out by the merger, they produce an intense flash of gamma rays, the most energetic form of light. Two opposite cones of blinding brilliance stab outward, announcing to the universe that a black hole has been born and is unleashing its power. This burst of gamma rays is staggeringly bright, though it lasts only a brief heartbeat by human standards. For perhaps a fraction of a second to 2 seconds at most, the collision pours out as much energy and gamma radiation as millions of suns would emit in their lifetimes. If we happen to be situated along the path of one of these jets, we witness this event as a short gamma ray burst, one of the most luminous explosions known. In the darkness of space, a burst like this outshines an entire galaxy for its fleeting duration. It is a cosmic lighthouse, suddenly ignited, then just as quickly snuffed out. Yet these jets are fickle beacons. Their message is highly directional, aimed only along the narrow paths they blaze. If Earth lies in the direct line of a jet, the gamma ray burst arrives without warning and dominates the sky for its brief life, a torrent of energy from across the cosmos. But if we are offset from the jet's path, the burst may pass unnoticed, a cosmic drama unfolding just out of sight. The jet's light is so tightly focused that even a slight misalignment leaves us in relative darkness. In fact, in the 2017 merger, astronomers on Earth saw only a faint glimmer of gamma rays and a delayed rise of other light because we were not looking straight down the barrel of the jet. It's a reminder that the universe can be broadcasting a spectacular event, but whether we catch it depends entirely on our vantage point in the cosmic auditorium. After the initial flash, the twin jets continue to surge outward, drilling into the interstellar medium, the tenuous gas between the stars. As they do, they begin to widen and slow down, their furious energy gradually dispersing into the surrounding space. This interaction produces afterglows. As the jets plow into and heat the interstellar gas, that gas in turn emits X-rays, radio waves, and other forms of light for days, months, even years after the merger. What starts as a focused flash evolves into a spreading plume of energy that can illuminate the collision's location long after the gamma rays have faded. In time, even observers who weren't aligned with the original beam might detect the jet's presence, not through the initial burst, but through this blooming afterglow that follows. For all their violence and brilliance, the jets carry away only part of the story of the neutron star collision. While these narrow beams race ahead, the merger has also flung out a great spherical tide of debris in all directions. This neutron-rich debris, much heavier and slower moving than the jets, is now expanding outward as an incandescent cloud. As the jets dim and vanish into the distance, that cloud of ejected matter begins to shine on its own timetable. In the aftermath of the burst, an eerie glow starts to blossom around the site of the merger, a different kind of cosmic beacon. It is a great fireball, an expanding shell of radioactive debris from the collision, and it will cast a fading but hauntingly beautiful light as it expands and cools. At the heart of the collision's aftermath, an immense cloud of debris billows outward, glowing with an otherworldly fire. This is the kilonova, an event fainter than the blinding gamma-ray burst, but in many ways more enduring and revealing. In the first day after the merger, the expanding cloud shines with a hot, bluish hue, powered by the incredible heat of freshly ejected matter. It's as if a miniature, fast-fading star has been born at the site of the collision, a point of light swelling and flickering in the darkness of its host galaxy. What fuels this eerie luminosity is the decay of freshly forged atoms. The neutron-rich matter flung out from the merger undergoes a frenzy of nuclear reactions as it expands and cools. In those cooling ashes, new elements are being created, not the light elements that stars typically fuse, but some of the heaviest atoms in the periodic table. Gold, platinum, uranium, iodine. Dozens of heavy elements congeal out of the neutron-rich soup in a cascade of rapid nuclear captures. These newborn atoms are often unstable, and as they decay radioactively, they release heat that warms the surrounding material. Like hot embers keeping a fire alive, this radioactivity sustains the kilonova's glow even as the debris cloud thins out. The result is a cosmic light bulb that gradually dims, its power source coming from the atomic transformations taking place within the expanding cloud. In the initial hours, the kilonova's light is dominated by the hottest, fastest moving ejecta. That's when its color is a vivid electric blue, a sign of extremely high temperatures. But as time marches on, heavier elements in the cloud begin to assert their presence. These heavy atoms are adept at blocking and absorbing light, especially the bluer hues and ultraviolet radiation. As they permeate the cloud, the visible light shifts toward longer wavelengths. Within a couple of days, the kilonova's early blue glow morphs into a rich crimson. What began as a bluish flame becomes a somber red ember, cooling and fading with each passing night. This transformation unfolds over a short span of time. The kilonova likely reaches its peak brightness only a day or two after the merger. Then it steadily wanes. Over a week or so, it diminishes significantly, the once brilliant fireball receding back into the blackness of space. Unlike a typical supernova, which can shine for weeks or months, this kilonova is brief, a flash by cosmic standards, yet still far longer lived than the split-second gamma-ray burst that preceded it. At its height, it might not rival a supernova's brilliance, but it is still astonishing. It can outshine millions of ordinary stars and be visible across hundreds of millions of light years. Then, inexorably, it decays, the light sliding from red into deeper infrared, and finally into darkness. Still, for those few days of its life, the kilonova is a spectacle to behold. Imagine gazing at a distant galaxy and seeing a new pinprick of light bloom on its edge, a spark that wasn't there the night before. Through telescopes, astronomers watch this point of light change color and fade, fully aware that they are witnessing alchemy on a cosmic scale. Every glimmer from that fading fireball carries information, the signature of exotic elements forming and decaying, the imprint of physical conditions never recreated on Earth. In its gentle glow, the kilonova tells a story of creation born from destruction. As the expanding debris finally cools, and its light fades away. It leaves behind more than just the memory of a brilliant flash. Scattered into the surrounding space are the freshly minted heavy elements, cast out like seeds from a cosmic garden. In time, these atoms, gold and silver, platinum and plutonium, xenon and europium, and so many others, will drift through their host galaxy. They may one day become part of new stars, new planets, or even new living beings, contributing to the cosmic ecosystem. The kilonova is not merely an ending, it is also a beginning, an enrichment of the universe's chemical tapestry, forged in a brief, furious glow, and then sent on its way. The spectacle of a kilonova is as fleeting as it is magnificent. To catch it in its full glory, one must be looking at precisely the right time. By the time this cosmic fireball's light reaches Earth, there is not a moment to lose. The challenge of capturing such an ephemeral event calls for vigilance and swift action. Astronomers have learned to prepare and respond quickly. As soon as there is any sign that a neutron star merger has occurred, perhaps an alert from gravitational wave detectors or a burst of high-energy light, telescopes around the world must swivel toward the patch of sky in question. A global network of eyes, on Earth and in space, stands ready to seize these fleeting photons before they fade. It's a carefully choreographed race against time, a dance of discovery in which humanity opens multiple windows onto the event. Through these windows, different types of telescopes and detectors, we aim to catch every possible clue from the merger, ensuring that even the briefest cosmic fireworks can be witnessed and understood by those of us watching from so far away. On an otherwise ordinary day on Earth, a most extraordinary signal quietly arrived. In a long L-shaped observatory buried in Washington state, laser beams shivered ever so slightly, a sign that space itself was stretching and squeezing. Across the United States in Louisiana and over in Italy, similar whispering tremors appeared at nearly the same moment. The gravitational wave observatories LIGO and Virgo had just sensed the telltale ripples of a distant neutron star collision. Within seconds, computers recognized the distinctive rising chirp pattern of two neutron stars spiraling together and issued an automated alert to astronomers worldwide. A message flashed across astronomers' networks. A gravitational wave event had been detected, likely the merger of two neutron stars, pinpointed to a broad region of the sky. The first messenger had spoken, a faint tremor in space-time, and it was a call to action for observers everywhere. Almost at the same time, a satellite orbiting Earth picked up a flash of high-energy light from that same general region of the sky. NASA's Fermi Gamma Ray Space Telescope recorded a short, faint burst of gamma rays lasting barely 2 seconds. It was the kind of signal expected from a neutron star merger's jet, a short gamma ray burst, but this one was weaker than typical. Still, the coincidence in timing was astounding. The gamma burst occurred only 1.7 seconds after the gravitational wave chirp. Two messengers, gravitational waves and gamma rays, arriving almost hand in hand from the same cosmic event. At once, astronomers knew they were on the verge of something historic. Telescopes across the world pivoted to heed the call. The race was on to find the exact location of the merger and witness the light of the ensuing explosion before it faded away. Pinpointing the aftermath of a collision in the vastness of space, however, is no simple task. The gravitational wave detectors could only tell astronomers a very rough patch of sky where the event likely occurred, an area spanning hundreds of square degrees, somewhere in the blurry intersection of the fields seen by the different observatories. Within that large patch lay countless stars and perhaps thousands of galaxies. The challenge: find the one galaxy, and within it, the one new pinpoint of light that hadn't been there before. Astronomers mobilized like an army of detectives canvassing a city. Teams on every continent began scanning the estimated region. Some used wide-field telescopes to tile the sky, taking image after image of different sectors of the search area. Others prioritized known galaxies in that region, thinking it likely that the merger's glow would appear in a galaxy relatively near to us, rather than in the inky black between galaxies. Every strategy was put into play because time was of the essence. The kilonova's light was expected to evolve and dim rapidly. Night was falling in Chile and South Africa, bringing those prime observing locations into darkness and into play. Around the globe, eyes turned upward. It was in Chile, under the pristine dark skies of the Andes, that the prize was found. At the Las Campanas Observatory, a small 1-meter telescope, relatively modest by today's standards, was employed to snap images of a galaxy called NGC 4993, one of the nearer galaxies in the suspect region. A young astronomer examining the digital images noticed something unusual in the outskirts of that galaxy. In a comparison between the new image and archived images of NGC 4993, a tiny dot of light stood out in the new one that had not been present before. It was a pinpoint of brilliant blue light, nestled against the hazy glow of a galaxy that was otherwise full of only old, reddish stars. This was no ordinary variable star or known supernova. It was something new, appearing right when and where the gravitational waves and gamma rays indicated it should. Within minutes, messages flew across the world. The optical counterpart had been spotted. The elusive kilonova was no longer theoretical. It was there, shining faintly in that image from Chile, a cosmic spark that hadn't been there a day earlier. A wave of excitement swept through the global astronomy community. Telescopes large and small were quickly trained on NGC 4993 to verify and study this new source. Observatories in Chile, with larger mirrors, as well as others in Australia, South Africa, and Asia that could see the target, all swung into action, sometimes within hours of the initial find. Even telescopes that were designed for other purposes joined the effort. The source was confirmed: a new transient light in NGC 4993, almost certainly the afterglow of the neutron star merger. Spectrographs soon began dissecting the light of the kilonova, splitting it into rainbows to read the chemical signatures. Early on, the object was indeed a vibrant blue, confirming it was extremely hot. But the spectra were strange. They were not clean lines of familiar elements as seen in ordinary stellar explosions. Instead, there were broad bumps and valleys, indications that a soup of heavy elements was absorbing chunks of the light. This was exactly what theorists expected if a host of freshly made heavy atoms, like cesium, tellurium, xenon, were present in the ejector. Over the next nights, as observers watched, the blue glow began to fade, and a more golden-orange hue crept in, then deepened to red. By about 3 days after the merger, the kilonova had transitioned to a cherry-red color, dimmer but still detectable. Multiple infrared observatories, including the Hubble Space Telescope and telescopes in Chile and Hawaii, kept watching as well. In the infrared spectrum, where cooler debris shines, the kilonova continued to glow even after it became faint to human eyes, revealing the heat from radioactive decays within the cloud. All these observations, the changing colors, the fading brightness, the spectral fingerprints, lined up beautifully with the theory of a neutron star merger kilonova. It was as though the data were tracing the script scientists had long written. A hot blue fireball dominated by lighter heavy elements early on, transitioning to a redder glow as the heaviest, light-blocking elements took over. Nor were these discoveries confined to visible light and infrared. While optical astronomers celebrated the kilonova's capture, high-energy astronomers were chasing the fading echoes of the jets. The gamma-ray burst, detected initially, had been surprisingly faint, leading scientists to suspect that the jets were not pointed directly at us. To test this, NASA's Chandra X-ray Observatory and ESA's Integral Gamma X-ray Observatory both monitored the location of NGC 4993. For days, they saw no X-rays coming from the merger site, a notable absence, since a typical on-axis short gamma burst would have an X-ray afterglow almost immediately. But patience paid off. About 9 days after the merger, Chandra picked up a feeble X-ray signal from the location of the fading kilonova. In the following days, it brightened slightly. At around the same time, radio telescopes, including the Very Large Array in New Mexico, detected a faint radio signal from the same spot. These late-arriving signals were the final confirmation of a picture that had been forming. The neutron-star merger had indeed launched ultra-fast jets, but because those jets were not pointing directly toward Earth, their initial high-energy emissions missed us. Only as the jets ploughed into surrounding interstellar material, slowing down and widening out, did their energy start to be emitted in all directions, eventually reaching our line of sight as a delayed X-ray and radio glow. This was a triumph of prediction as well. Scientists had anticipated that an off-axis jet would behave this way, and nature delivered the proof. In the end, the concerted efforts of countless astronomers and dozens of telescopes gave us an unprecedented panoramic view of a neutron-star collision. Within a matter of days, humanity had detected this event in gravitational waves, literally hearing the converging stars ring spacetime like a drum. We had seen the burst of gamma rays from the jets that heralded the birth of a black hole. We had watched the kilonova's visible and infrared light bloom and fade, witnessing the birth of heavy elements in real time. And finally, we caught the faint whispers of X-rays and radio waves as the jets made themselves known to us from across the cosmic void. Never before had so many messengers, from light to gravity's ripples, been captured together for a single event. It was the first true multi-messenger observation in the history of astronomy, a cosmic symphony in which each instrument, each wavelength and wave, played its part. With the event thoroughly recorded from every angle, the task of understanding truly began. Scientists around the world pored over the troves of data, comparing what was seen and heard with what their theories and models had predicted. Piece by piece, they examined the gravitational wave signal, the timing of the gamma rays, the luminosity and spectra of the kilonova, the emergence of the X-ray and radio afterglow. And as the analysis proceeded, an astonishing realization grew. The universe's performance was matching the theoretical predictions to a remarkable degree. The long-anticipated phenomena, from the rising chirp of the gravitational waves to the 2-second gamma flash, from the blue to red kilonova glow to the delayed X-ray afterglow of off-axis jets, it was all there, unfolding almost exactly as scientists had envisioned. Nature's script and the scientist's script were in harmony. The stage was set to truly link theory with reality, to measure just how right or wrong our understanding had been, and to learn whatever new lessons this event had to teach. At last, theory and observation met face to face in the light of a neutron-star collision. For decades, astrophysicists had plotted and speculated about these events, predicting the gravitational wave chirps, the gamma-ray flashes, the dimming glow of a kilonova, the formation of a black hole. Now those predictions were confronted with real data, and the correspondence was extraordinary. The cosmic story that unfolded in the skies matched, in so many respects, the story that had been written in scientific journals and simulated on supercomputers. It was a moment of validation, showing that human intuition and mathematics had managed to glimpse the truth of a spectacular cosmic process before we ever observed it. Consider the origin of the heavy elements, one of the great unsolved questions that theory had attempted to answer. For years, scientists suspected that neutron star mergers could be the crucibles in which elements like gold, platinum, and uranium are forged, perhaps even more abundantly than in the explosions of ordinary supernova. The glow of the kilonova provided the long-sought proof. The way its light shifted from blue to red and the specific pattern of colors observed in its spectrum were like a fingerprint of exotic atomic nuclei decaying. It was smoking gun evidence that in those expanding debris clouds, the universe was minting its treasure trove of heavy elements. No longer was it just theory. We now could say with confidence that the gold in our jewelry, the platinum in our electronics, even elements vital to life like iodine, likely owe their existence to ancient neutron star collisions. The cosmic forge that theory had envisioned was real, and we watched it in action, tying our very material existence to these distant stellar catastrophes. Then there were the bursts of energy themselves. Astronomers had long theorized that short gamma-ray bursts, those mysterious sub-2-second flashes of high-energy light, were triggered by merging neutron stars. It was a compelling idea, but without direct evidence, it remained an educated guess. That uncertainty vanished with the nearly simultaneous detection of gravitational waves and a short gamma-ray burst from the same event. In that moment, the connection was cemented. We both heard the inspiraling dance of the neutron stars in gravitational waves, and we saw the flash of their jets in gamma rays. When telescopes later caught the delayed X-ray and radio afterglow creeping into view, it fit exactly the models of a jet seen off-axis, explaining why this burst was fainter and stretched out in time. Piece by piece, observation filled in the puzzle that theory had pieced together over years. Each new data point, the timing, the energies, the afterglow behavior, vindicated the predictions that had been made about these bursts. What was once an astronomical hypothesis is now a definitive fact. Short gamma-ray bursts are born in the death throes of merging neutron stars. Even the gravitational waves themselves carried a wealth of information that bridged theory and reality. Subtle details in the waveform, how the signal swelled in frequency and then abruptly cut off, spoke volumes about the final moments of the neutron stars. From these imprints, scientists could infer the radii and deformability of the stars, teasing out clues about the state of ultra-dense matter in their cores. The data suggested that neutron star matter isn't perfectly rigid. Under sufficient mass, it will deform and ultimately succumb to collapse, just as theoretical models had predicted. In fact, the very outcome of the merger, a hypermassive neutron star that lived briefly, then became a black hole, pointed to a specific threshold for neutron star stability. The observations indicated a maximum mass on the order of about 2.5 times the Sun's mass, beyond which no neutron star can survive without collapsing. This value lined up with many prior theoretical estimates derived from nuclear physics and pulsar observations. Furthermore, Einstein's general relativity earned yet another gold star. The gravitational waves travelled at essentially the speed of light, arriving at Earth within 2 seconds of the gamma rays, despite a 130 million-year journey. There was no sign of exotic deviations or violations of relativity, just as Einstein's century-old theory had predicted. Time and again, in aspect after aspect, the universe behaved as our best physical theories said it should. This convergence of theory and reality is a triumph for science, a celebration of human understanding, but it is also a beginning. Each successful prediction that the event confirmed now becomes a foundation on which to build even deeper questions. With one example of a neutron star merger observed in such detail, astronomers are already refining their models, checking where they might have wiggle room for the unexpected. Perhaps the next neutron star collision we observe will surprise us, showing a quirk of physics we didn't anticipate, or an outcome slightly different due to different masses or spins. In fact, the 2017 event itself left a few puzzles that theory must now address, such as the hint of a delayed collapse, that extra second of hypermassive life, and the mysterious X-ray glow that persisted long after the merger, which could be from a shock or material falling into the new black hole. Every observation not only tells us you were right, but also whispers, here's something new to learn. Most profoundly, the successful capture and explanation of this event ushers us into a new era of astronomy, the era of multi-messenger observation. We are no longer confined to studying the cosmos through light alone. We can now listen to the vibrations of space-time, and someday, perhaps even catch particles like neutrinos from these cataclysms. The collision of two neutron stars in 2017 was the first time humanity both heard and saw a cosmic event in unison. It validated decades of effort. Engineers and scientists who built sensitive gravitational wave detectors, astronomers who coordinated rapid response systems, theorists who prepared the roadmaps. It is an affirmation that when we open more than one window onto the universe, we gain a far richer view. Even the briefest cosmic whisper, a 2-second flash, a half-minute chirp of gravity, can be transformed into an epic narrative when we have the tools to capture it from all sides. As this chapter of our journey draws to a close, we find that the once hypothetical spectacle of neutron star collisions has become a tangible reality we can witness. The light and the fury, the gravity and the matter, they came together and told us a story, one we had long imagined, but only now finally heard with our own ears and seen with our own eyes. Yet, this is far from the final chapter. In truth, it feels like an introduction to a much larger saga. With each new collision that the cosmos presents, we will test the limits of our understanding and undoubtedly encounter new mysteries. The universe, ever the master storyteller, surely has more surprises in store for us. We stand on a threshold where observation feeds theory and theory guides observation, each neutron star merger a beacon lighting our way to deeper knowledge. The next act is already out there, waiting in the stars. And we, the eager observers, remain ready to chase the light and ride the ripples of space-time, to follow the cosmic fireworks and the quiet murmurs of gravity wherever they lead us, as our journey through the cosmos continues onward.